Hello there and welcome to Just About Earth, where curiosity slows down, questions stretch out comfortably, and science takes a gentler path toward rest. I'm glad you're here, wherever here happens to be for you tonight. Maybe you're listening while the lights are low, or perhaps the day is just beginning, and the world outside hasn't quite decided what it's going to do yet. Either way, you've arrived at a quiet place, and that's enough for now. Tonight, I'd like to invite you to think about a part of our planet that almost never raises its voice, a place that doesn't advertise its history with ruins or road signs or layers of visible rock stacked neatly along a cliff face, a place that keeps nearly everything it knows buried, pressed down, sealed off, and locked away under ice so thick it bends the earth beneath it. Antarctica. A continent that feels distant not just in miles but in time. When we picture it, most of us imagine endless white, howling winds, research stations clinging to the edge of survival, and penguins navigating a world that seems almost deliberately inhospitable. It feels like a place that belongs to the present moment, or maybe to the extremes of climate change discussions, but rarely to deep history. And yet, what if that assumption is wrong? What if Antarctica is not just a frozen backdrop at the end of the world, but a missing chapter in Earth's story? Not a footnote, not a frozen afterthought, but a section torn out, folded over, and hidden beneath kilometres of ice. A chapter written when the planet looked different, when climates behaved differently, when life spread across regions that now seem unimaginable. There's something quietly unsettling about the idea that a whole continent could be holding on to information we've barely begun to read. Not because it's gone, but because it's been preserved too well, locked away behind conditions that make access slow, expensive, and rare. So before we go any further, let me ask you something gently. Where are you listening from tonight? A city apartment? A quiet house? A long drive? Or maybe somewhere between sleep and waking? And what time is it there really? Not just what the clock says, but how it feels in your body right now. Because the story we're easing into tonight isn't about rushing forward. It's about slowing down enough to notice what has been waiting for millions of years. If you find this kind of wandering curiosity calming, or if it gives your mind something soft and steady to rest on, you might consider liking the video or subscribing. It helps this small, quiet corner reach other people who could use a moment of calm too. And now, with nothing pressing us forward, let's begin to drift into the story itself. Antarctica wasn't always this way. That sentence alone can feel strange, because the image of Antarctica as permanently frozen is so deeply ingrained that it's hard to imagine it as anything else. Ice defines it. Cold explains it. Isolation protects it. But none of those things are permanent features of Earth. They're conditions, temporary states in a planet that has never stopped changing. Long before humans ever wondered what lay at the bottom of the world, Antarctica occupied a very different role. It wasn't the silent observer it is now. It was active, connected, and once, astonishingly, alive in ways that feel incompatible with its modern image. To understand why Antarctica might hold a missing chapter of Earth's history, it helps to remember how unevenly we've read the planet so far. Most of what we know about Earth's past comes from places that are easy to reach. Mountain ranges where rock layers are exposed. River valleys that cut through sediment like open books. Deserts where erosion reveals ancient surfaces instead of hiding them. Antarctica offers none of these conveniences. Nearly its entire surface is buried beneath ice that, in some places, is over 4 kilometers thick. That ice doesn't just sit there, it flows slowly but relentlessly, pressing down with enormous force, reshaping the land beneath and protecting it at the same time. What's under that ice hasn't been weathered by rain, chewed up by roots, or disturbed by human construction. It's been sealed. This makes Antarctica frustrating and tantalizing in equal measure. From a scientific perspective, it's like knowing there's a library somewhere, but every book is locked inside a vault made of frozen water. You can see hints of what's inside. You can measure shapes, detect outlines, and listen for echoes using radar and seismic waves. But actually opening the pages takes time, patience, and technology that didn't even exist until recently. For most of human history, Antarctica wasn't just unread. It was almost entirely unknown. When early explorers imagined a southern continent, they didn't picture ice. They imagined balance. Ancient geographers believed that land in the north had to be countered by land in the south, a symmetry that made sense philosophically even if no one had proof. This imagined landmass, sometimes called Terra Australis, appeared on maps long before anyone set foot there. It was a placeholder, a guess, a suggestion that the world wouldn't tip over if there were too much land on one side. And when Antarctica was finally seen, mapped, and named, it didn't match those early expectations at all. Instead of fertile land, it revealed a continent that seemed almost deliberately resistant to human presence. That resistance shaped how we thought about it. Antarctica became a place of limits. The coldest temperatures, the strongest winds, the driest deserts hidden beneath ice. It became defined by extremes, and extremes have a way of flattening nuance. When a place is described as inhospitable, we tend to stop asking what it used to be. We focus instead on what it prevents, and yet geology doesn't care about comfort. The rocks beneath Antarctica formed under conditions that had nothing to do with polar night or sub-zero winds. They formed when this land was somewhere else entirely. The continents, as you know, are not fixed. They drift slowly across the planet's surface, carried on massive tectonic plates that move at roughly the speed your fingernails grow. Over millions of years, those tiny movements add up to oceans opening, mountains rising, and climates shifting dramatically. Antarctica was once part of a much larger arrangement of land known as Gondwana, a southern supercontinent that included what are now Africa, South America, Australia, India, and parts of the Middle East. In that ancient configuration, Antarctica was not isolated at the bottom of the world. It was connected, central, and influenced by climates very different from the one it experiences today. There was a time when Antarctica sat farther north, bathed in milder temperatures, receiving sunlight that supported plant life. Fossil evidence tells us that forests once grew there, not sparse, struggling vegetation clinging to survival, but dense, thriving ecosystems with trees, ferns, and complex food webs. This isn't speculation or fantasy. It's based on physical remains pulled from the edges of the continent and from sediment layers exposed where ice has retreated. Pollen grains, leaf impressions, and fossilized wood have all been found, preserved well enough to tell a story that feels almost surreal when you picture it against today's frozen landscape. These discoveries hint at something important. If Antarctica once supported forests, animals, and complex ecosystems, then it also recorded climate patterns, extinction events, and evolutionary transitions that may not be preserved anywhere else. As the continent drifted southward and global climates cooled, life there would have faced enormous pressure to adapt, migrate, or disappear. Those transitions didn't happen all at once. They unfolded over millions of years, leaving traces in sediment, rock, and eventually ice. And because Antarctica became isolated so early and so thoroughly, those traces may be less disturbed than in regions that remained active, inhabited, and reshaped by later geological events. This is where the idea of a missing chapter becomes more than a metaphor. Earth's history is not evenly distributed across its surface. Some periods are well documented in certain places and nearly absent in others. The rise and fall of ancient climates, the movement of species between continents, and the timing of major shifts in atmospheric composition are all topics where the data is incomplete. Antarctica sits at the intersection of many of these unknowns. It was present during critical transitions, positioned in ways that made it sensitive to global change, and then sealed off before later disturbances could overwrite the record. Ice itself plays a strange dual role here. On the one hand, it hides the past. On the other, it preserves it with extraordinary fidelity. Ice cores drilled from Antarctica contain layers that accumulate year after year, trapping tiny bubbles of ancient air. Those bubbles are literal samples of past atmospheres, frozen in place. By analysing them, scientists can reconstruct levels of carbon dioxide, methane, and other gases stretching back hundreds of thousands of years, sometimes more. This doesn't just tell us what the climate was doing, it tells us how fast it changed, how stable it was, and how closely temperature and atmospheric composition were linked long before humans entered the picture. But the ice is only part of the story. Beneath it lies bedrock that has been largely untouched since long before the ice arrived. Mountain ranges hidden under ice sheets, valleys carved by rivers that no longer exist, basins that once held lakes or shallow seas. All of these features can be detected indirectly, mapped using radar and gravity measurements, revealing a continent that is far more complex than its smooth, white surface suggests. Antarctica is not a flat slab of ice. It's a rugged landscape with its own deep geography, one that formed under conditions that no longer exist there. What makes this especially intriguing is how Antarctica's isolation may have allowed certain records to survive that were erased elsewhere. On other continents, tectonic activity, erosion, and biological processes constantly recycle the surface. Old rocks are buried, melted, or broken down. Antarctica's deep freeze slowed many of those processes to a crawl. In some regions, it may have acted like a planetary archive, storing information in conditions that favoured preservation over renewal. That doesn't mean everything is intact or easily interpreted, but it does mean that the continent has the potential to answer questions that have lingered for decades. Questions like how quickly Earth can shift between climate states, how ecosystems respond to prolonged cooling, what happens to a continent when it becomes isolated at a pole, and how life adapts or fails to adapt when sunlight patterns change dramatically. Antarctica's position makes it uniquely sensitive to changes in Earth's orbit, tilt, and rotation, factors that influence glacial cycles over long time scales. Those cycles are written into the ice and the land beneath it, waiting for careful interpretation. There's also a human element to this curiosity, even if humans never lived there during those ancient times. We're storytellers by nature. We want narratives that feel complete, arcs that make sense. When there's a blank space on the map or a gap in the record, it pulls at us. Antarctica has always been one of those blanks, not just geographically, but historically. We know it matters. We just haven't known how much, or in what way. As technology improves, the pace of discovery increases, but it does so quietly. There are no dramatic unveilings, no sudden revelations that rewrite everything overnight. Instead, there are slow accumulations of data. A new ice core here, a refined radar map there, a fossil found at the edge of a retreating glacier. Each piece adds detail, texture, and context. Over time, patterns begin to emerge, connections form, and the idea that Antarctica holds a missing chapter of Earth's history starts to feel less speculative and more inevitable. What's especially interesting is that this story doesn't belong solely to the past. The processes that shaped Antarctica then are still shaping the planet now. Climate shifts, atmospheric changes, ocean circulation, and ice dynamics are not relics. They're ongoing. Understanding how they unfolded in the past helps us understand how they might unfold again under different circumstances. Antarctica becomes not just a record of what was, but a reference point for what could be. Long before anyone tried to describe it with numbers, before satellites traced its outline or icebreakers tested its edges, Antarctica earned its reputation quietly. It didn't announce itself with towering ruins or fossil beds exposed to the sky. It didn't invite curiosity in the way deserts do, with bones and stones laid bare by erosion. Instead, it learned early how to hide, and over time that hiding became its defining feature. From a distance, the continent appears almost simple, a vast sweep of white. A smooth, uninterrupted surface that seems to offer very little information. That simplicity is deceptive. What looks empty is actually layered. What appears still is slowly moving. What seems lifeless is carefully preserving records of extraordinary change. Antarctica doesn't erase its past, it buries it. And in doing so, it keeps secrets in a way no other place on Earth quite manages. One reason those secrets have lasted so long is scale. Antarctica is enormous, larger than Europe, nearly twice the size of Australia, and yet, unlike other continents, its defining material is not rock or soil, but ice. Roughly 90% of the world's ice sits here, holding about 70% of the planet's fresh water locked in frozen form. In places, the ice sheet rises higher than many mountain ranges elsewhere on Earth. That ice presses down on the land beneath with immense weight, flattening, reshaping, and protecting it at the same time. The result is a continent that is both revealed and concealed by the same substance. Ice behaves differently from stone. It flows. Slowly, almost imperceptibly but constantly. Under its own weight, it creeps outward toward the coast, carrying with it anything trapped inside. Dust, ash from ancient volcanic eruptions, pollen from forests that no longer exist. Tiny bubbles of air that formed before humans ever looked at the sky and wondered what it was made of. These materials aren't scattered randomly. They settle into layers year after year, forming a vertical timeline that can be read from top to bottom, if you know how to look. But the ice also acts as a shield. It seals off the surface below from wind, rain, and biological activity. In most parts of the world, the land is constantly being rewritten. Rivers carve new channels. Plants break apart rock. Animals burrow and disturb sediment. Humans build, dig, and reshape almost everything they touch. Antarctica escaped most of that. Not because it was protected by intention, but because it was protected by conditions. The cold arrived early enough and stayed long enough to limit interference. Once the ice sheets expanded, they created a barrier that few forces could penetrate. This makes Antarctica frustrating for exploration, but invaluable for preservation. It's not that the continent contains more history than others, it's that so much of its history hasn't been overwritten. The pages weren't torn out or scribbled over. They were closed and placed on a shelf made of ice. That shelf, however, is not uniform. Antarctica is divided into two very different regions, separated by the Transantarctic Mountains, a vast range that cuts across the continent like a spine. East Antarctica is older, more stable, and thicker with ice. West Antarctica is younger, more fragmented, and geologically active. Beneath West Antarctica lies a complex network of basins, some of them below sea level, hidden under ice that floats in places and rests on rock in others. This difference matters because it affects how the ice behaves, how stable it is, and how much information it has preserved. East Antarctica's ice sheet is ancient. Parts of it may have persisted for tens of millions of years, surviving periods when global temperatures were higher than today. That longevity makes it one of the most important climate archives on the planet. Drilling deep into this ice allows scientists to extract cores that extend far beyond the reach of records from Greenland or mountain glaciers elsewhere. These cores don't just show temperature changes, they reveal patterns in atmospheric circulation, volcanic activity, and even shifts in Earth's orbit that influence long-term climate cycles. West Antarctica tells a different story. Its ice sheet is more dynamic, more sensitive to changes in ocean temperature and sea level. Beneath it lie rift systems and volcanic regions, some of which are still active. Heat from below interacts with ice above, creating complex conditions that influence how fast ice moves and how likely it is to retreat. This region doesn't just preserve history, it participates in it. The processes happening there today echo changes that occurred in the past, offering a living laboratory for understanding how ice sheets respond to warming. Yet even with all this complexity, Antarctica gives very little away freely. The cold is relentless. Temperatures can drop low enough to freeze exposed skin in minutes. Winds scour the surface, reshaping snow into hard, sculpted forms that resist movement. Darkness lasts for months at a time, followed by continuous daylight that disrupts sleep and perception. These conditions don't just challenge human endurance, they limit the tools we can use and the time we can use them. Every expedition requires planning, funding, and an acceptance that progress will be slow. Because of that, much of what we know about Antarctica comes not from direct observation, but from indirect measurement. Radar systems mounted on aircraft send signals through ice and record what bounces back. Gravity measurements detect variations in mass that hint at mountains, valleys, and buried basins. Seismic waves generated by small explosions or natural earthquakes travel differently through rock and ice, revealing structures hidden far below. Piece by piece, scientists assemble maps of a continent they may never physically touch in most places. Those maps have already revealed surprises. Vast mountain ranges buried beneath ice sheets, rivaling the Alps in size. Deep valleys carved by rivers that flowed when Antarctica was warmer and wetter. Networks of subglacial lakes, some of them as large as inland seas, sealed beneath kilometres of ice and isolated from the surface for millions of years. These lakes aren't frozen solid. Pressure and geothermal heat keep them liquid, creating environments unlike anything else on Earth. Studying them raises questions not just about Earth's past, but about the limits of life itself. Secrecy, in Antarctica's case, isn't deliberate, it's emergent. The continent doesn't hide because it wants to, but because the conditions there favour concealment over exposure, and that concealment has shaped the way humans relate to it. Antarctica has never been owned in the traditional sense. No permanent indigenous population lived there. No ancient cities rose and fell. No agriculture reshaped the land. When humans finally arrived, it was late and it was brief. Exploration, scientific research, and seasonal habitation define our presence. We are visitors, not heirs. This lack of long-term human disturbance is rare. It means that Antarctica's history is almost entirely natural. The stories written there were composed by tectonic plates, atmospheric circulation, ocean currents, and biological evolution. They weren't edited by agriculture or industry. That purity, if it can be called that, makes the continent invaluable as a reference point. When scientists want to understand what Earth systems do without human interference, Antarctica offers one of the closest approximations available. But even that is changing. The modern world reaches everywhere, eventually. Climate change is altering Antarctica's ice dynamics. Warming oceans are thinning ice shelves from below. Glaciers are accelerating in some regions, delivering more ice to the sea. These changes don't erase the past, but they do affect how accessible it is. As ice retreats in certain areas, it exposes land that hasn't seen sunlight for millions of years. That exposure creates opportunities for discovery, but it also risks damage. Once exposed, ancient surfaces can weather rapidly. The very act of revealing a secret can destroy it. This creates a tension that runs through Antarctic science. The desire to know more must be balanced against the need to preserve what remains. Drilling ice cores, sampling sediments, and exploring subglacial environments all carry risks. Contamination is a constant concern. Introducing modern microbes into ancient ecosystems could alter them irreversibly. Even footprints can last for decades in such a dry, cold environment. Antarctica's secrets are fragile, not because they are delicate, but because they are rare. There is also the matter of time itself. Antarctic processes operate on scales that are difficult to grasp. Ice sheets advance and retreat over tens of thousands of years. Mountain ranges rise and erode over millions. The continent's current frozen state is relatively recent in geological terms, yet it feels eternal to us. That mismatch between human perception and planetary timescales contributes to the sense that Antarctica is unknowable. We expect answers quickly. Antarctica responds slowly. When scientists talk about Antarctica holding missing chapters of Earth's history, they aren't suggesting a single revelation waiting to be uncovered. There is no one secret hidden beneath the ice that will suddenly make everything clear. Instead, there are countless small records, each contributing a sentence, a paragraph, or a page. Together they can fill gaps in our understanding of how Earth transitioned between different climate states, how continents influenced ocean circulation, and how life responded to extreme environmental change. For example, Antarctica played a key role in the development of the modern Antarctic circumpolar current, a massive ocean current that flows uninterrupted around the continent. This current isolates Antarctica thermally, preventing warmer waters from reaching its shores. Its formation marked a turning point in global climate, contributing to the growth of Antarctic ice sheets and influencing temperature patterns worldwide. Understanding when and how that current developed requires evidence from the seafloor around Antarctica and from sediments beneath the ice. Those records are incomplete elsewhere. Here, they may be preserved. There are also unanswered questions about mass extinctions and evolutionary bottlenecks. When climates cooled and Antarctica froze, what happened to the species that lived there? Did some migrate northward, influencing ecosystems on other continents? Did others adapt to cold conditions in ways that left genetic traces in modern species? Fossils found in Antarctica suggest connections between ancient southern ecosystems that are still not fully understood. Each new discovery adds context, but also raises new questions. Even the ice itself contains stories that go beyond temperature. Chemical signatures trapped in ice layers reveal changes in atmospheric circulation, dust transport, and even distant volcanic eruptions. Ash layers from volcanoes thousands of kilometers away can be found embedded in Antarctic ice, providing timestamps that link events across the planet. In this way, Antarctica acts as a global recorder, capturing signals from far beyond its borders. What makes this especially compelling is that many of these records extend into periods of Earth's history that are otherwise poorly documented. The further back you go, the rarer continuous climate records become. Antarctica pushes that boundary further than almost anywhere else. It allows scientists to test models of Earth's behaviour over long timescales, checking whether our understanding of climate dynamics holds up when confronted with deep time. And yet, despite all this, Antarctica remains resistant to narrative closure. Every answer it provides feels provisional. The continent gives just enough information to suggest patterns, then recedes again into silence. That's part of what keeps it compelling. It refuses to be simplified. It resists being reduced to a single story. Perhaps that's why Antarctica occupies such a unique place in human imagination. It's not just remote, it's incomplete. We sense that there is more to know, but we also sense that knowing will always be partial. The white surface becomes a symbol of that incompleteness, a reminder that the planet still holds knowledge beyond our reach. It can feel almost impossible to imagine Antarctica as anything other than it is now. The mind resists the idea. Ice feels permanent. Cold feels defining. The sheer scale of the frozen surface gives the impression that it has always been this way, that the continent emerged fully formed as a white expanse and simply stayed there, unmoving and unchanged. But that impression is misleading, and the deeper you look into Earth's history, the more it dissolves. There was a long stretch of time when Antarctica did not belong to the cold world we associate it with today. It belonged to a warmer Earth, one where coastlines lay in different places, where oceans flowed along unfamiliar paths, and where the idea of polar ice would have seemed strange. During that time, Antarctica was not a frozen margin. It was part of the living, breathing surface of the planet, shaped by sunlight, rainfall, and biological activity. To understand this version of Antarctica, It helps to stop thinking in terms of modern geography. Continents are not fixed reference points. They are passengers on tectonic plates, drifting slowly but relentlessly across the planet's surface. Over hundreds of millions of years, these movements rearrange the world in ways that would be unrecognizable if we could watch them unfold in real time. Antarctica's journey through those shifts is what transformed it from a green land into the frozen archive it is now. Long ago, Antarctica was joined to other southern continents in a vast landmass that stretched across much of the southern hemisphere. This connection mattered. Landmasses influence climate simply by existing. They redirect winds, alter ocean currents, and affect how heat moves around the globe. When Antarctica was connected to its neighbours, it shared their climates, their ecosystems, and their evolutionary pathways. Warm air could circulate freely across it. Ocean currents behaved differently. Seasonal light patterns were still extreme, but not yet paired with the deep cold that would later dominate the region. Fossil evidence tells us that Antarctica once supported forests, not sparse or stunted growth, but extensive plant life adapted to long summer days and long winter nights. Tree fossils found along the continent's margins reveal species related to those that once thrived in what are now temperate regions. These trees grew tall, forming canopies and shedding leaves that accumulated into soil. Beneath them lived insects, reptiles, and early mammals, all participating in ecosystems that functioned much like those elsewhere on Earth at the time. One detail that often surprises people is that these forests endured months of darkness each year. Even when Antarctica was warmer, its position near the pole meant it still experienced long polar nights. Life adapted. Plants evolved strategies to survive prolonged darkness. Growth surged during continuous summer daylight, compensating for winter dormancy. This wasn't an alien environment. It was challenging, but it was workable, and life found ways to thrive within it. The presence of these ecosystems tells us something important about Earth's climate during that period. Global temperatures were higher, atmospheric carbon dioxide levels were elevated compared to today. Ice caps were minimal or non-existent. The poles were cool relative to the equator, but not frozen wastelands. This warmer world persisted for tens of millions of years, long enough for complex ecosystems to establish themselves and evolve. As Antarctica slowly drifted southward, subtle changes began to accumulate. The continent's movement altered how it interacted with surrounding oceans. Connections to other landmasses weakened, then broke entirely. These separations didn't happen overnight. They unfolded over millions of years, each shift nudging the climate in a new direction. Ocean gateways opened and closed. Currents were rerouted. Heat distribution across the planet began to change. One of the most significant consequences of Antarctica's isolation was the development of an uninterrupted ocean current circling the continent. This current acted like a thermal barrier, preventing warmer waters from reaching Antarctica's coast. As that barrier strengthened, temperatures dropped. Snow that once melted seasonally began to persist year-round. Ice sheets started to form, first modestly, then with increasing scale and permanence. For the ecosystems that had once thrived there, these changes were devastating. Plants adapted to warmth and moisture found themselves facing colder conditions and shorter growing seasons. Animals dependent on those plants either migrated, adapted, or disappeared. Over time, Antarctica transitioned from a place of growth to a place of accumulation, where snow built up faster than it melted and ice slowly claimed the landscape. What makes this transformation especially important is that it did not erase everything that came before it. As ice advanced, it buried soils, river valleys, and forest floors. In doing so, it preserved them. Organic material trapped beneath the ice decomposed slowly, if at all. Sediments settled and remained undisturbed. In some regions, entire landscapes were effectively sealed off, frozen in a state that reflects conditions from a world that no longer exists. This is where Antarctica's value as a historical record becomes clear. Other continents experienced similar climate transitions, but their records were overwritten. Rivers continued to flow, mountains eroded, life kept moving, recycling materials and reshaping surfaces. Antarctica's deep freeze interrupted that cycle. It didn't stop geology entirely, but it slowed it dramatically. The result is a continent that still carries traces of its green past, not on the surface, but beneath layers of ice that act like a protective cover. Scientists studying Antarctic geology often describe a sense of working backward through time. Each metre of ice drilled reveals older conditions. Each layer of sediment sample tells a story about temperature, vegetation, and atmospheric composition. Fossil pollen grains recovered from beneath ice sheets are especially valuable. They are small, durable, and highly specific to certain plant types. By identifying them, researchers can reconstruct entire ecosystems, including the types of trees present, the density of forests, and the prevailing climate conditions. What these reconstructions show is not a sudden freeze, but a gradual decline. Antarctica did not go from green to white overnight. There were long periods of cooling punctuated by warmer intervals. Ice advanced, retreated, and advanced again. Forests shrank toward the coast. Species migrated northward in waves. Each stage left traces, layered one atop another, creating a complex record of adaptation and loss. There is also evidence that Antarctica's green past influenced ecosystems far beyond its borders. As species migrated away from the cooling continent, they carried genetic lineages with them. Connections between southern continents can still be seen in modern plant and animal distributions. Certain species found in South America, Australia, and Africa share ancestry that points back to a time when Antarctica acted as a bridge rather than a barrier. These connections matter because they help explain patterns that would otherwise seem coincidental. Why certain plant families appear on distant continents. Why similar fossil species show up in places now separated by vast oceans. Antarctica's role in these patterns has often been underestimated simply because its own fossil record is harder to access. But as more evidence emerges, it becomes clear that the continent was once a central player in the biological history of the Southern Hemisphere. The climate story recorded in Antarctica's transition also provides context for present-day concerns. The planet has shifted between warm and cold states many times before. Antarctica's green past shows that polar regions can support life under the right conditions. Its frozen present shows how sensitive those regions are to changes in ocean circulation and atmospheric composition. Understanding how quickly Antarctica froze and what conditions triggered that shift helps scientists assess how stable the current ice sheets really are. It's worth noting that Antarctica's forests did not resemble modern tropical rainforests. They were adapted to cooler temperatures and extreme light cycles. Growth rings in fossilised wood indicate periods of rapid summer growth, followed by long winter dormancy. These details matter because they show how life adjusted to polar conditions without ice. They also suggest that the loss of these ecosystems was not due to darkness alone, but to sustained cooling that exceeded their ability to adapt. As ice sheets expanded, they reshaped the land beneath them. Valleys were deepened, mountains were worn down, rivers were replaced by glaciers that followed similar paths but operated on entirely different timescales. In some cases, ice followed ancient river channels, preserving their outlines even as it erased their original function. Today, radar mapping reveals these buried landscapes, allowing scientists to trace the contours of a world that existed before ice dominated the scene. There is something quietly unsettling about these discoveries, not because they imply catastrophe, but because they remind us how temporary any state of the planet really is. Antarctica's frozen identity feels stable because it exists on timescales longer than human history. But from a geological perspective, it is just one phase in a long sequence. Before it was frozen, it was green. And before it was green, it was something else entirely. This doesn't mean Antarctica will return to that state anytime soon, The conditions that supported ancient forests were shaped by a configuration of continents and oceans that no longer exists. Still, the fact that such a transformation happened at all expands our sense of what is possible. It reminds us that the planet's systems are interconnected, and that changes in one region can ripple outward in ways that take millions of years to fully play out. At some point in Earth's long history, Antarctica began to separate itself not just emotionally, as it feels today, but physically. This wasn't a dramatic tearing away that anyone could have witnessed, even if someone had been there to watch. It was quieter than that, slower, the kind of change that only becomes obvious after millions of years have passed, and the consequences have already settled in. Antarctica didn't choose isolation. It drifted into it, carried along by forces that operate far beneath the surface, indifferent to forests, animals, or future observers. To understand how a continent can drift away from the rest of the Earth, it helps to let go of the idea that the planet's surface is solid in the way we experience solidity. The crust beneath your feet feels immovable, because on a human timescale it mostly is. But beneath that crust lies a layer that behaves more like a very slow-moving fluid. Tectonic plates float on this layer, jostling, colliding, and pulling apart over immense spans of time. These movements are measured in centimetres per year, but given enough time, they rearrange entire continents. Antarctica's journey began when it was still firmly attached to its southern neighbours. Land connected land. Rivers crossed what are now oceans. Species moved freely across regions that today feel impossibly distant from one another. This connectivity shaped evolution, climate and geography in ways that are still visible if you know where to look. But that configuration was never permanent. Heat from Earth's interior kept the plates in motion, and stresses built up along their boundaries. The first signs of separation were subtle. Rifts formed, stretching the crust thinner in some places. Magma rose to fill the gaps, cooling into new rock that recorded the direction and timing of movement like a geological timestamp. Over time, these rifts widened. What had once been a continuous landmass developed fractures, then channels, then shallow seas. Antarctica was no longer fully connected, but it was not yet alone. As these separations progressed, Antarctica's relationship with the rest of the planet began to change in important ways. Land connections act as bridges not just for organisms, but for heat. When continents are connected, warm air and ocean currents can travel across them or along their edges more easily. Breaking those connections disrupts those pathways. Antarctica started to experience a different climate not because it suddenly moved far south, but because the systems that once shared warmth with it were gradually withdrawn. The opening of ocean gateways was particularly important. As Antarctica separated from adjacent land masses, new passages allowed seawater to flow in directions it hadn't before. These openings didn't just change local conditions, they altered global circulation patterns. Oceans are one of the planet's primary mechanisms for distributing heat. Redirecting them has far-reaching consequences, especially at the poles. As Antarctica drifted farther south, it crossed thresholds that mattered. The amount of sunlight it received changed. Seasonal contrasts intensified. Long periods of daylight were followed by long periods of darkness year after year. While life had already adapted to these cycles, the cooling that accompanied isolation made adaptation harder. Plants that had survived polar light patterns now had to cope with dropping temperatures and changing precipitation. Animals that relied on those plants faced the same challenge. Drifting also changed Antarctica's internal dynamics. As it moved, stresses built up within the continent itself. Mountain ranges rose in response to tectonic forces, even as erosion slowly worked to wear them down. These mountains influenced weather patterns, redirecting winds and snowfall. Some regions became colder and drier than others, setting the stage for uneven ice formation once conditions allowed it. What's important to remember is that Antarctica didn't become isolated in a single step. It went through long transitional phases where it was partly connected, partly separated and experiencing climates that fluctuated between familiar and increasingly hostile. These transitions left complex records in the rocks and sediments beneath today's ice. Layers formed during warmer intervals sit alongside layers formed during cooler ones, each telling a slightly different story about what the continent was experiencing at the time. As separation continued, Antarctica's oceans began to dominate its climate more than its land connections ever had. Surrounded increasingly by open water, the continent became exposed to powerful circumpolar winds. These winds reinforced ocean currents that flowed endlessly around the continent, rather than toward it. Warm water that might once have reached Antarctic shores was deflected away. Cold water circulated continuously, reinforcing the chill. This was a turning point. Once that circumpolar flow became established, Antarctica's isolation was no longer just geographical, it was thermal. The continent became cut off from the planet's heat-sharing systems in a way no other landmass was. This didn't instantly create ice sheets, but it pushed the climate in that direction. Snow that fell was less likely to melt. Glaciers that formed were more likely to persist. As ice began to accumulate, it fed back into the system. Ice reflects sunlight more effectively than land or water. As white surfaces expanded, more solar energy was bounced back into space, reinforcing cooling. This feedback loop accelerated the transformation. Antarctica's drift had set the conditions. Ice locked them in. From a geological perspective, Antarctica's isolation was not an accident. It was a consequence of predictable processes playing out over vast timescales. But from a biological and climatic perspective, it was a dramatic shift. A continent that had once been integrated into the global system became something closer to a self-contained world. Life that remained had to adapt to increasingly extreme conditions. Much of it didn't. What makes this story especially compelling is how clearly it illustrates the interconnectedness of Earth's systems. Antarctica didn't freeze simply because it moved south. It froze because movement changed ocean currents, which changed heat distribution, which changed atmospheric circulation, which changed snowfall patterns. No single factor acted alone. Each change amplified the others. The drift also helps explain why Antarctica holds such an unusual geological record. As it became isolated, erosion slowed. Biological activity diminished. Weathering processes that constantly reshape other continents were muted. Ice took over as the dominant force, but ice is selective in how it alters the land. It scours some areas deeply, while leaving others relatively untouched. It buries as much as it erases. The result is a patchwork of preservation and modification that is unlike anything found elsewhere. In many places beneath the ice, ancient surfaces remain intact. River valleys carved when Antarctica was warmer still exist, now filled with ice instead of water. Sediments laid down in shallow seas before full separation remain trapped beneath frozen layers. These features provide clues not just about Antarctica's own past, but about the configuration of the entire planet during those transitional periods. The idea of a continent drifting away can feel abstract, but its consequences are tangible. Antarctica's isolation shaped the evolution of Southern Ocean ecosystems. It influenced global sea levels. It affected atmospheric composition by changing how carbon was stored and circulated. Even today, the presence of a massive ice-covered continent at the South Pole influences weather patterns thousands of kilometers away. What's striking is how long these consequences take to fully unfold. Antarctica's separation began tens of millions of years ago, but some of its most dramatic effects are still ongoing. Ice sheets continue to respond to changes in ocean temperature. Glaciers still flow along pathways determined by ancient topography. The continent's position continues to shape global circulation in ways that scientists are still working to fully understand. In this sense, Antarctica never really finished drifting away. Its physical movement slowed as plates settled into their current positions, but its climatic and systemic separation remains active. It is still responding to forces set in motion long ago. It is still influencing the rest of the Earth, even as it appears distant and disconnected. Finding fossils in Antarctica sounds at first like a contradiction. Fossils are usually associated with exposed rock, dry ground, cliffs, deserts, or eroded hillsides where layers of Earth's past are laid bare by wind and time. Antarctica offers none of that on the surface. Instead, it presents a nearly unbroken skin of ice, thick enough to hide entire mountain ranges and deep valleys, thick enough to make the idea of buried forests feel more like imagination than evidence. And yet, fossils are there. Not scattered openly, not easy to collect, but present all the same, quietly confirming that the frozen continent once carried life very different from what we see today. The discovery of Antarctic fossils did not begin deep in the interior. It began at the margins, in places where ice retreats just enough to reveal rock beneath. Coastal outcrops, mountain peaks that pierce through ice sheets, and areas scoured by glaciers have provided the first glimpses. These places are rare, isolated, and often accessible only for brief windows of time. But when scientists reached them and began to look closely, what they found challenged the long-held image of Antarctica as a place without a biological past. Among the most striking discoveries were fossilized plant remains, leaves pressed into stone, fragments of wood turned to mineral, pollen grains trapped in sediment. These were not the remains of cold-adapted mosses or sparse tundra plants. They belonged to trees, shrubs, and ferns that require far milder conditions to survive. Some fossils showed growth rings, clear and regular, indicating seasonal cycles of growth and dormancy. Others revealed leaf structures adapted to capturing sunlight efficiently, an important trait in regions with long summer days and long winter darkness. The presence of these fossils immediately raised questions. How warm did Antarctica have to be for forests to grow there? How long did those conditions last? And how did life respond as temperatures gradually declined? Each fossil offered a piece of the puzzle, but none of them told the whole story on their own. One of the most valuable types of evidence comes not from large dramatic fossils, but from microscopic ones. Pollen grains are remarkably durable. Their outer shells are resistant to decay, and their shapes are distinct enough to identify plant families and even specific genera. By extracting sediment samples from beneath ice or from exposed rock layers, scientists can analyze pollen assemblages and reconstruct ancient vegetation with surprising precision. These analyses have revealed that Antarctica once supported forests dominated by species related to modern southern beeches and conifers. These trees formed dense stands, not isolated pockets. Understory plants filled the spaces between trunks. Soil developed through the accumulation of organic matter, supporting complex ecosystems. Insects pollinated plants. Rivers carried nutrients. This was not a marginal environment clinging to survival at the edge of habitability. It was a functioning landscape. What makes these findings especially compelling is their age. Many Antarctic plant fossils date to periods tens of millions of years ago, long before the ice sheets that now dominate the continent formed. This places them in a time when global climates were warmer and more stable than today, when polar regions played a very different role in Earth's climate system. Antarctica was not a refrigerator. It was part of the planet's active biosphere. As the continent drifted south and ocean circulation patterns changed, these ecosystems began to face increasing stress. Cooling temperatures shortened growing seasons. Snow lingered longer. Ice appeared first at higher elevations and in shaded regions, then expanded outward. Fossil records suggest that forests retreated gradually, not disappearing all at once. Some plant species persisted longer than others, adapting as best they could to changing conditions. The fossils capture this transition. In older layers, pollen diversity is high, indicating a rich mix of plant types. In younger layers, diversity declines. Certain species disappear. Others become more dominant, suggesting that only a subset of plants could tolerate the cooling climate. Eventually, even those hardy species vanished, leaving behind sediments that record a landscape increasingly shaped by ice rather than vegetation. These changes did not occur in isolation. As plants disappeared, animals dependent on them were forced to respond. Fossils of insects and small vertebrates are rarer in Antarctica, partly because conditions for preservation are more limited. But the available evidence suggests that many species migrated northward as habitats deteriorated. Antarctica's role as a biological corridor reversed. Instead of connecting southern continents, it became a source of dispersal away from the pole. The idea that Antarctica once hosted forests also reshapes how we think about polar darkness. Months without sunlight sound uninhabitable, yet these ancient ecosystems thrived despite that challenge. The key difference was temperature. Cold amplifies darkness by slowing biological processes. In a warmer world, plants could afford long dormant periods. Animals could store energy and resume activity when light returned. Once temperatures dropped below certain thresholds, that balance collapsed. The whispers of these lost forests are not limited to fossils alone. They echo in the structure of the land beneath the ice. Radar mapping has revealed networks of ancient river valleys carved into bedrock, valleys that would have required sustained flow over long periods. Rivers do not carve such features under ice. They require rainfall, surface runoff, and unfrozen ground. These buried valleys align with regions where fossil plant evidence has been found, reinforcing the picture of a once green continent shaped by water rather than ice. There is also chemical evidence. Organic molecules preserved in sediments beneath ice sheets carry signatures of plant life. Certain compounds are associated with leaf waxes and woody tissues. When detected in Antarctic samples, they confirm that vegetation once covered areas now sealed off from the surface. These molecules persist even when larger structures have been destroyed, providing another line of evidence that complements fossil remains. The challenge, of course, is access. Drilling through kilometers of ice to reach sediment layers is a complex and expensive endeavor. Each drill site must be carefully chosen to minimize environmental impact and maximize scientific return. Equipment must operate reliably in extreme cold. Samples must be kept uncontaminated. Progress is slow by necessity. But with each successful extraction, the picture becomes clearer. What emerges is a sense of Antarctica as a place that did not simply lose its forests, but recorded their disappearance with unusual clarity. Elsewhere on Earth, transitions from forested landscapes to glaciated ones are often obscured by subsequent activity. Ice advances and retreats multiple times. Vegetation returns and reshapes the land. Human activity adds another layer of disturbance. In Antarctica, once ice took over, it rarely relinquished its grip. That stability preserved the moment of change. These fossil records are valuable not just for understanding Antarctica itself, but for understanding how ecosystems respond to long-term climate change. The shift from green continent to frozen desert was driven by gradual changes, not sudden catastrophe. It involved feedback loops between temperature, ice cover, and atmospheric composition. Studying how plants and animals responded then provides context for changes occurring now, even though the circumstances are different. There is also a broader evolutionary story embedded in these fossils. Many plant lineages found in Antarctica's past still exist today, but their modern distributions reflect the continent's loss. Southern beech forests, for example, are now found in South America, Australia, and New Zealand, regions that were once connected to Antarctica. Fossil evidence suggests that Antarctica was a central hub for these lineages, not a peripheral outpost. Its freezing reshaped global biodiversity patterns by removing that hub. This perspective challenges the tendency to view Antarctica as a passive backdrop in Earth's history. It was not merely affected by global change, it helped drive it. The growth of Antarctic ice sheets altered sea levels worldwide. The loss of Antarctic forests influenced carbon storage and atmospheric composition. These changes fed back into global climate, affecting regions far from the pole. The idea of lost forests beneath the ice also changes how we think about preservation. Ice is often associated with destruction, grinding landscapes down and erasing features. In Antarctica, ice did both. It reshaped the surface dramatically, but it also shielded what lay beneath. In places where ice moved slowly or remained cold-based, meaning it stayed frozen to the ground rather than sliding, underlying sediments were left relatively intact. These conditions allowed fossils to survive in remarkable condition. Some of the most intriguing discoveries come from erratic rocks, stones carried by glaciers and deposited far from their origin. Embedded within these rocks are fossil fragments that hint at the landscapes they passed through. By tracing the paths of glaciers backward, scientists can infer where those fossils came from, even if the original source remains buried. It is a form of indirect exploration, using ice itself as a messenger from the past. There is a quiet irony in this. The same ice that buried Antarctica's forests is now one of the primary tools for discovering them. Glaciers transport evidence from hidden regions to accessible ones. Ice cores preserve atmospheric records that contextualize biological change. Without the ice, much of this history would have been lost to erosion long ago. As research continues, the picture grows more detailed but also more complex. Not all regions of Antarctica followed the same path. Some areas cooled earlier, others retained pockets of vegetation longer. Elevation, proximity to the coast, and local geography all played roles. This patchwork transition adds nuance to the story, reminding us that continental scale change is never uniform. What remains consistent is the sense that Antarctica's biological past was richer and more influential than its present suggests. The fossils beneath the ice are not anomalies. They are remnants of a long-lived phase in the continent's history, one that shaped life across the southern hemisphere and left marks that persist today. As attention turns increasingly toward what lies beneath the ice, the methods used to uncover these stories continue to evolve. New drilling technologies, improved remote sensing, and refined analytical techniques promise to reveal even more. But each discovery also reinforces the same underlying truth. Antarctica is not empty. It is quiet. And beneath that quiet lies evidence of a world that once thrived, waited, and then slipped slowly into stillness, leaving behind whispers rather than monuments, preserved not in ruins, but in stone, sediment, and ice that continues to move inch by inch across the memory of a greener Earth. When people talk about ancient climates, they often imagine dusty rocks, cracked earth, or sun-bleached fossils sitting under an open sky. Climate history feels like something written into deserts, canyon walls, or layers of exposed sediment where time stacks itself neatly for us to read. Antarctica breaks that expectation completely. Here, the story of climate is not laid out in stone. It is sealed, pressed downward, layered vertically instead of horizontally, locked inside frozen water that has been falling from the sky year after year for longer than human civilization has existed. What makes Antarctica unique is not just that it is cold now, but that it became cold in a way that preserved the transition. Snow fell, compacted, turned to ice and stayed there. It did not melt and flow away seasonally. It accumulated. Each year added a thin layer, sometimes barely noticeable, sometimes thicker depending on storms and temperature. Over tens of thousands of years, those layers stacked into kilometers of ice, forming one of the most detailed natural records of climate the planet has ever produced. This ice is not uniform. It is a vertical archive. The deeper you go, the older it gets. Near the surface, layers may represent individual years or even seasons. Deeper down, pressure compresses those layers, thinning them, squeezing time closer together. But even under immense weight, the sequence remains. Older ice stays beneath younger ice. The order is preserved. What makes this ice extraordinary is not just its age, but what it contains. As snow fell, it trapped tiny pockets of air. These bubbles were sealed off as the snow compacted into ice, preserving samples of Earth's atmosphere exactly as it was at the time they formed. Not approximations, not chemical guesses inferred from rock, actual air, oxygen, nitrogen, carbon dioxide, methane, all frozen in place. When scientists drill ice cores in Antarctica, they're not just collecting frozen water, they're collecting time capsules. Each segment of core corresponds to a specific period in Earth's climate history. By analysing the gases inside those bubbles, researchers can determine atmospheric composition stretching back hundreds of thousands of years, and in some cases, over 1 million years. This matters because climate is not just about temperature, it is about balance. How much carbon dioxide was in the air, how methane levels rose and fell, how dust moved through the atmosphere, how volcanic eruptions injected particles that cooled the planet temporarily. All of these factors leave fingerprints in the ice. For example, during colder periods known as glacial stages, carbon dioxide levels were consistently lower. During warmer interglacial periods, they rose. This pattern appears again and again in Antarctic ice cores, revealing a tight relationship between greenhouse gases and temperature long before human industry existed. The ice does not debate this relationship, it records it. But Antarctica's frozen climate record goes beyond gases. The ice itself carries information about temperature through subtle variations in the water molecules that make it up. Water is composed of hydrogen and oxygen, but not all atoms of these elements are identical. Some are slightly heavier than others. The ratio of these isotopes changes depending on temperature. Warmer conditions favour one balance, colder conditions favour another. By measuring these isotope ratios in ice layers, scientists can reconstruct past temperatures with remarkable accuracy. This allows them to map climate fluctuations over time, identifying cold snaps, warming periods, and long transitions that unfolded over thousands of years. Antarctica does not just tell us that climate's changed. It tells us how fast, how often, and how extreme those changes were. One of the most striking findings from Antarctic ice cores is how regular some climate cycles have been. Over the past several 100,000 years, Earth has moved through repeated glacial and interglacial periods. Ice advanced, then retreated. Temperatures dropped, then rose. These cycles align closely with changes in Earth's orbit and tilt, subtle variations that affect how sunlight is distributed across the planet. What Antarctica shows is how sensitive the climate system is to relatively small shifts. Changes in sunlight distribution triggered feedback loops involving ice cover, atmospheric gases, and ocean circulation. Once those loops began, they amplified the initial signal, driving the planet toward colder or warmer states. The ice preserves this process layer by layer, showing how gradual changes can lead to dramatic outcomes. Another feature locked into Antarctic ice is the record of volcanic activity. When volcanoes erupt, they eject ash and sulfur particles high into the atmosphere. Some of this material eventually settles out, falling onto ice sheets thousands of kilometers away. In Antarctica, these volcanic layers appear as thin bands rich in specific chemical compounds. By identifying and dating these layers, scientists can link climate changes to volcanic events. Some eruptions cause short-term cooling by reflecting sunlight. Others coincided with shifts in atmospheric circulation. These layers also serve as time markers, allowing researchers to synchronize Antarctic records with records from other parts of the world. A volcanic eruption recorded in Greenland ice can often be matched to the same event in Antarctica, tying together the climate histories of both hemispheres. Dust is another important clue. During colder, drier periods, more dust was carried by winds and deposited on the ice. This dust often originated from distant continents such as South America or Australia. Its presence reveals changes in wind patterns, vegetation cover, and aridity far from Antarctica itself. The ice becomes a global recorder, capturing signals from across the planet. What is especially valuable about Antarctica's climate archive is its continuity. Many climate records elsewhere are interrupted. Ice melts, sediments are eroded, layers are disturbed. Antarctica's interior ice sheets have remained stable enough to preserve uninterrupted sequences spanning immense stretches of time. This continuity allows scientists to see long-term trends rather than isolated snapshots. One of the most important revelations from this record is how unusual the present moment is. For hundreds of thousands of years, carbon dioxide levels fluctuated within a relatively narrow range. Even during the warmest natural periods, they never exceeded certain thresholds. The rapid increase observed in the modern era stands out sharply against this background. In Antarctic ice cores, the spike is unmistakable. This does not mean the planet has never been warmer than today. It has. Antarctica itself was once ice-free. But the pace of change recorded in recent layers is different. The ice shows how quickly atmospheric composition has shifted compared to natural variations. It provides context, scale, and proportion that cannot be gained from short-term measurements alone. Beyond the ice cores themselves, Antarctica preserves climate history beneath the ice as well. Sediments trapped under ice sheets record earlier phases, before permanent ice formed. These sediments contain chemical signals, microfossils, and mineral assemblages that reflect ancient ocean temperatures and circulation patterns. Extracting them is far more challenging than drilling ice, but the rewards are substantial. These sub-ice records extend the climate story further back, into periods when Antarctica was transitioning from a green continent to a frozen one. They show how ocean temperatures dropped, how currents shifted, and how ice began to stabilize. Together with ice cores, they create a layered narrative that spans tens of millions of years. What emerges from this frozen archive is not a static picture, but a dynamic one. Climate did not change smoothly. It lurched, it oscillated, it responded to multiple influences at once. Antarctica's ice captures this complexity without simplifying it. Each layer is a moment, but also part of a larger pattern. There is also an important silence in the record. Certain changes that dominate modern climate discussions do not appear in older ice layers. Human influence is absent. Industrial pollutants are missing. The baseline is natural variability. This silence is as informative as any signal, because it defines what Earth's climate system looks like without us. Working with this frozen archive requires patience. Ice cores are drilled slowly, often taking multiple seasons to complete. Samples must be kept frozen at all times to preserve their integrity. Analysis takes years. Interpretations are refined as techniques improve. There are no dramatic revelations overnight. Instead, there is accumulation, layer by layer, just like the ice itself. Antarctica's climate record is also vulnerable. As surface temperatures rise, some regions experience increased melting. Ice shelves thin. Flow patterns change. While the deep interior remains cold and stable for now, coastal areas are already losing ice that may contain valuable records. Once melted, that information is gone forever. This adds urgency to the work, but not haste. Rushing risks contamination and misinterpretation. Antarctica rewards careful study, not speed. The continent has waited millions of years. It does not respond well to impatience. What is striking when looking at these frozen records is how often Earth returned to balance after disruption. Glacial periods ended, warm periods cooled, feedback loops reversed. The climate system has resilience built into it. But it also has limits. Antarctica's ice sheets grew because certain thresholds were crossed. Once established, they became stable, reinforcing cold conditions for millions of years. This stability is part of why Antarctica feels timeless. The ice gives the impression of permanence, but the record within it tells a different story. Change is constant, stability is temporary. Even the most massive ice sheet is the result of conditions aligning, not an unchanging state. When most people picture Antarctica, the image that comes to mind is flat, endless, a white surface stretching in all directions with nothing to interrupt it but wind and shadow. It feels reasonable to assume that a place buried under so much ice must be smooth beneath it, scraped down to something close to featureless by millions of years of freezing. That assumption turns out to be very wrong. Beneath Antarctica's ice lies a landscape as dramatic, varied and extreme as any on Earth, and in some cases more so. Hidden under kilometres of ice are mountain ranges that rival, and sometimes exceed, those visible on other continents. Valleys plunge deeper than the Grand Canyon is tall. Ridges stretch for hundreds of kilometres, unseen by human eyes, yet shaping everything above them. Antarctica is not a flat continent with ice poured on top. It is a rugged world that just happens to be wearing an exceptionally thick coat. The discovery of these buried mountains did not come from hikers or climbers. No one stumbled across them by accident. They were revealed gradually, through indirect methods that allow scientists to see through ice without removing it. Radar systems mounted on aircraft send signals downward. Those signals pass through ice but bounce back when they hit rock. By measuring the time it takes for the signal to return, researchers can calculate how deep the rock lies and what shape it has. Over years of surveys, these measurements have been stitched together into detailed maps of Antarctica's hidden terrain. What those maps revealed was startling. Instead of a simple bedrock surface, scientists found vast mountain systems completely concealed beneath the ice sheet. One of the most significant is the Gamburtsev mountain range, a chain of peaks roughly the size of the European Alps, buried beneath East Antarctica. Some of these mountains rise more than 3 kilometres from their base to their peaks, yet none of them break the surface. They are entirely entombed in ice. The existence of such a range raises immediate questions. Mountains do not simply appear. They form through tectonic processes, often involving collisions between plates or intense compression of Earth's crust. The Gamburtsev Mountains likely formed hundreds of millions of years ago, long before Antarctica froze. At that time, they would have stood exposed, subject to erosion, weather and life. Rivers would have cut into them. Forests may have grown on their slopes. Over time, those processes should have worn them down, and yet they remain tall, preserved, shielded from erosion by ice that arrived early enough to halt the normal cycle of wearing down. In a strange way, Antarctica's freezing protected its mountains from disappearing. The ice did not flatten the land so much as freeze it in place. Other buried features are even more extreme in scale. Beneath West Antarctica lie deep basins, some extending more than 2 kilometres below sea level. These basins are not just low. They are vast, sprawling depressions carved by ancient rivers and glaciers, then later deepened by tectonic stretching. If the ice were removed, parts of West Antarctica would be underwater, forming archipelagos rather than a single landmass. The depth of some of these valleys is difficult to grasp. The Grand Canyon, impressive as it is, reaches about 1.6 kilometres at its deepest point. Some Antarctic valleys exceed that depth from ice surface to bedrock, and that measurement does not even account for how much deeper the valleys extend below sea level. These are features shaped over immense spans of time, then hidden so completely that their existence was unknown until the late 20th century. The presence of such dramatic topography beneath the ice has profound implications. Ice does not behave the same way over flat ground as it does over rugged terrain. Mountains slow ice flow, valleys channel it, ridges create pressure points that influence how glaciers move, where they thicken and where they thin. The ice sheet above Antarctica is not sliding smoothly like a blanket. It is interacting constantly with the landscape beneath it. In some regions, ice flows rapidly along deep troughs carved into bedrock, forming fast-moving glaciers that deliver ice to the coast. In others, ice is nearly stationary, frozen to the ground, barely moving at all. These differences matter because they affect how stable the ice sheet is and how it responds to warming. Understanding the hidden landscape is essential to understanding the future of Antarctic ice. The mountains also influence climate at a local scale. Even buried, they affect how cold air pools, how snow accumulates, and where ice thickens. Elevated regions tend to be colder, encouraging ice to persist. Depressions can trap warmer air or allow ocean heat to penetrate farther inland beneath ice shelves. These interactions create a complex three-dimensional system where geology and climate are inseparable. There's another layer to this story that reaches even deeper into time. Many of Antarctica's buried mountains and valleys were shaped before ice dominated the continent. Their forms reflect processes that occurred when Antarctica was warmer and wetter. River networks carved valleys, weathering softened slopes. These features are relics of a different climate regime, preserved beneath ice that arrived later. Radar images of the bedrock show patterns that are unmistakably fluvial. Meandering channels, branching tributaries. These are not the chaotic gouges left by glaciers. They are the signatures of flowing water. This tells us that before Antarctica froze, it experienced sustained rainfall and surface runoff. Rivers flowed long enough and powerfully enough to carve deep valleys, some of which now guide the movement of ice. In this sense, Antarctica's buried mountains and valleys act like fossils of climate. They record not just what the land looked like, but how it functioned. A landscape shaped by rivers implies temperatures above freezing, precipitation falling as rain, and a hydrological cycle very different from the one that exists today. These features corroborate fossil evidence of forests and reinforce the idea that Antarctica once supported complex ecosystems. The ice that later covered these landscapes did not erase them completely. In some places, it enhanced them. As glaciers advanced, they followed existing valleys, deepening them further. In other places, cold-based ice, frozen to the ground, slid very little and preserved the underlying terrain almost perfectly. The result is a patchwork where some areas show heavy glacial modification, while others look remarkably ancient. This uneven preservation adds complexity to the record. Scientists must determine which features predate ice and which were shaped by it. Doing so requires combining radar data with seismic studies, gravity measurements, and modelling. Each method provides a different piece of information. Together they allow researchers to reconstruct the sequence of events that shape the continent. What emerges is a picture of Antarctica as a place with a deep geological memory. Its mountains tell stories of continental collisions and separations. Its valleys speak of rivers that no longer flow. Its basins hint at tectonic stretching and volcanic activity. All of this history is still there, beneath the ice, influencing how the continent behaves today. These buried landscapes also help explain why Antarctica's ice sheet formed where it did. Elevated regions encouraged early ice accumulation. Once ice began to build, it flowed downhill into valleys, thickening and stabilizing. Over time, ice sheets grew outward from high ground, eventually covering nearly the entire continent. The shape of the land guided this process, determining where ice persisted and where it retreated during warmer intervals. Understanding this relationship between ice and bedrock is not just an academic exercise, it is essential for predicting future change. As oceans warm, ice shelves thin, and glaciers accelerate, the hidden topography will play a critical role in determining how quickly ice is lost. Valleys that slope inland can allow warm ocean water to reach far beneath the ice sheet, undermining it from below. Ridges can act as temporary barriers, slowing retreat, but only until they are breached. The fact that some of these valleys extend deeper than the Grand Canyon is tall underscores the scale of what is at stake. Ice sitting in deep basins below sea level is particularly vulnerable. Once retreat begins, it can become self-sustaining, with grounding lines moving inland and ice thinning rapidly. The landscape beneath Antarctica is not passive in this process. It shapes the outcome. There is also a quieter significance to these buried mountains. They remind us that Antarctica's apparent emptiness is deceptive. Beneath the uniform surface lies a world as structured and complex as any other. The absence of visible features does not indicate simplicity, it indicates concealment. In a way, Antarctica asks us to rethink how we define landscapes. We tend to equate visibility with importance. What we can see feels real, what is hidden feels abstract. Antarctica challenges that bias. Its most influential features are invisible. They guide ice flow, influence climate, and preserve history, all while remaining out of sight. As technology improves, the resolution of our maps improves with it. What were once vague outlines become detailed ridges and valleys. Features once dismissed as anomalies reveal coherent patterns. Each improvement brings Antarctica's hidden terrain into sharper focus, not as a curiosity, but as a central component of the planet's system. And yet, even with these advances, much remains unknown. Large areas of the continent have been mapped only coarsely. Some regions remain blank, especially in the deepest interior. The mountains and valleys there are inferred rather than seen. Their full shapes remain uncertain. Antarctica still holds parts of its landscape close, revealing them slowly on its own terms. Beneath the ice that defines Antarctica, beneath the buried mountains and deep valleys, there is another layer of the continent that feels almost impossible at first glance. Water. Not frozen solid, not briefly melted and refrozen, but liquid water, sealed away in darkness, pressure, and cold for spans of time that stretch far beyond human comprehension. These lakes do not sit under open skies. They do not reflect clouds or collect rain. They exist in complete isolation, hidden beneath kilometers of ice, untouched by sunlight for hundreds of thousands and in some cases millions of years. The idea of liquid water beneath one of the coldest places on Earth seems contradictory, but Antarctica has a way of forcing us to revise assumptions. Ice, despite its rigidity, is an excellent insulator. Deep beneath the surface, pressure increases dramatically. The weight of ice lowers the freezing point of water. Heat from Earth's interior, small but persistent, rises upward. Where these factors meet, ice does not always remain solid. Instead, it melts at the base, creating pockets and networks of liquid water trapped between ice and bedrock. These subglacial lakes were not discovered by chance. No one drilled into one blindly. Their existence was inferred long before they were confirmed. Radar surveys revealed unusually flat, smooth reflections beneath the ice, signatures that suggested liquid surfaces rather than rough rock. Seismic data supported the idea. Gravity measurements hinted at mass distributions consistent with water-filled cavities. Slowly, cautiously, the picture came into focus. Antarctica was hiding lakes, not a few, hundreds. Today, scientists have identified more than 400 subglacial lakes beneath the Antarctic ice sheet. Some are small, little more than ponds by surface standards. Others are enormous, stretching for tens or even hundreds of kilometres. The most famous of these is Lake Vostok, a body of water roughly the size of Lake Ontario, buried beneath nearly 4 kilometres of ice. For perhaps 15 million years, it has existed in complete darkness, sealed off from the atmosphere, untouched by seasonal cycles. What makes these lakes extraordinary is not just their isolation, but their stability. They are not transient meltwater pools that appear and vanish. Many of them are long-lived features, maintained by a balance of heat, pressure, and ice flow. Water melts at the base of the ice sheet in some areas, flows along bedrock channels and refreezes elsewhere. This creates a slow, hidden hydrological system that moves water beneath the continent, connecting lakes through channels that no human has ever seen directly. This hidden circulation matters. It lubricates the base of the ice sheet, affecting how glaciers move. Where water is present, ice can slide more easily over bedrock. Where it refreezes, ice thickens and becomes more resistant to motion. The distribution of these lakes and waterways influences which parts of Antarctica are stable and which are more prone to change. In this way, unseen water plays a quiet but powerful role in shaping the ice above it. But the lakes are not just physical features, they are environments. And environments, even extreme ones, raise an inevitable question. Is there life? For decades, the idea of life in subglacial Antarctic lakes was considered speculative at best. The conditions seemed too harsh. No sunlight, extremely low nutrient input, cold temperatures, crushing pressure. And yet, as scientists studied similar environments elsewhere, beneath glaciers in Greenland, under ice caps in the Arctic, and even in deep subsurface rock formations, a pattern emerged. Life, especially microbial life, is far more adaptable than once assumed. On Earth, organisms exist in deep mines, in hydrothermal vents, in acidic hot springs, and within solid rock. They do not rely on sunlight, they rely on chemistry. Energy can come from reactions between minerals and water, from the slow breakdown of organic material, or from geothermal processes. Subglacial lakes, isolated though they are, may provide just enough chemical energy to support microbial ecosystems. Evidence supporting this possibility has begun to accumulate. Samples taken from meltwater that refroze near the base of Antarctic ice sheets contain microbial DNA. Chemical analyses suggest metabolic processes consistent with life. These findings do not confirm thriving ecosystems in every subglacial lake, but they strongly suggest that some lakes are biologically active, even if that activity is slow and sparse. What makes this particularly intriguing is the timescale. If life exists in these lakes, it may have been isolated for millions of years. That isolation could have allowed microbial communities to evolve independently, adapting to conditions unlike any on the surface. Studying such organisms could offer insights into the limits of life on Earth and inform the search for life elsewhere, particularly on icy worlds like Europa or Enceladus, moons that also harbour subsurface oceans beneath thick ice. Accessing these lakes, however, is not straightforward. Drilling through kilometres of ice risks contaminating environments that have been sealed for geological timescales. Introducing surface microbes or chemicals could alter these ecosystems irreversibly. Because of this, scientists approach subglacial exploration with extreme caution. Clean drilling techniques have been developed, using sterile equipment and careful protocols to minimise contamination. Even so, each attempt is weighed carefully against the potential risk. One of the most significant breakthroughs came not from direct sampling of a lake, but from observing how lakes behave. Some subglacial lakes fill and drain over time, releasing water into downstream channels and refilling later. Satellite measurements have detected subtle changes in ice surface elevation associated with these events. Ice rises slightly as water accumulates beneath it, then sinks as water drains away. These movements are small, often just a few meters, but detectable with precise instruments. These observations revealed that Antarctica's subglacial water system is dynamic. Lakes are not static pools. They interact with each other, exchanging water over distances of hundreds of kilometers. This network influences ice dynamics on timescales of months to years, adding another layer of complexity to the continent's behaviour. The chemistry of subglacial lakes also provides clues about Antarctica's past. Water trapped beneath ice can dissolve minerals from bedrock, carrying signatures of the rocks it interacts with. By analysing these chemical profiles, scientists can infer the composition of the underlying geology, even in regions where direct sampling is impossible. In this way, lakes become indirect messengers from the buried landscape. Some subglacial lakes sit atop ancient sediment layers laid down when Antarctica was ice-free. These sediments may contain organic material, microfossils, and chemical records of ancient climates. If sampled carefully, they could extend our understanding of Antarctica's history far beyond what ice cores alone can provide. They may preserve evidence of ecosystems that existed before the ice arrived, frozen in time beneath the continent. There is also a temporal mystery associated with these lakes. Not all of them are equally old. Some formed relatively recently as ice sheets thickened and conditions changed. Others may have persisted through multiple glacial cycles, surviving periods when ice retreated and then advanced again. Determining the age of a subglacial lake is challenging, but it matters for understanding how stable these environments are and how they fit into the broader history of the continent. The sheer existence of these lakes challenges simple narratives about Antarctica. It is easy to think of the continent as inert, frozen, and lifeless. The reality is more complex. Beneath the ice, processes continue, water moves, chemical reactions occur, ice flows. The continent is not asleep. It is quiet but active. These hidden waters also force us to reconsider how ice sheets behave over long timescales. Traditional models often treated the base of ice sheets as either frozen or wet, with limited nuance. The discovery of extensive subglacial hydrological networks revealed a more intricate system. Water availability varies in space and time, influencing ice stability in ways that are still being incorporated into predictive models. This matters because Antarctica's future is closely tied to the behaviour of its ice. As global temperatures rise and oceans warm, changes at the ice base could accelerate ice loss. Warm water penetrating beneath ice shelves can increase melting, adding water to the subglacial system. That water can, in turn, speed up ice flow. Understanding how existing lakes and channels respond to these changes is critical for anticipating future sea level rise. At the same time, these lakes offer a rare opportunity to study environments untouched by human influence. In an age where few places on Earth remain truly isolated, subglacial Antarctic lakes represent some of the most pristine environments available for scientific study. They provide a baseline for understanding natural processes without the confounding effects of pollution, land use, or modern climate alteration. There is a quiet humility in studying these hidden lakes. Progress is slow, discoveries are incremental, instruments must be precise, mistakes can have lasting consequences. Antarctica does not yield its secrets easily, and its subglacial waters are among the most carefully guarded. And yet, the effort continues, not driven by spectacle, but by curiosity. Each new map of subglacial water pathways refines our understanding. Each chemical analysis adds depth to the picture. Each cautious exploration brings us closer to understanding how this continent functions as a system, from bedrock to ice surface. If Antarctica has a language of its own, it is written vertically, not in lines that run across the land, but in layers that descend straight down through ice that has been accumulating for unimaginable lengths of time. Each layer represents a moment, a season, sometimes a single year, pressed into place and protected by everything that came after it. And inside those layers, sealed with extraordinary care by pressure and cold, are tiny messages from the past. Air bubbles, so small they are easy to overlook, yet so rich in information that they have transformed how we understand Earth's history. An ice core is, at its simplest, a long cylinder of ice drilled out of an ice sheet, but that description does not do justice to what it represents. An ice core is not just frozen water, it is a continuous archive of snowfall, atmosphere, temperature, and chemistry stretching back hundreds of thousands of years, sometimes more. Unlike rock layers, which can be folded, broken, or eroded, ice layers in Antarctica are remarkably orderly. Snow falls, it settles, it is buried by more snow. Over time, the weight compresses it into firn, a granular intermediate stage, and eventually into solid ice. Throughout that process, the sequence remains intact. What makes this process so valuable is its consistency. In the cold, dry interior of Antarctica, snow does not melt and refreeze seasonally. It accumulates. That accumulation means that time is recorded without interruption. Each layer retains information about the conditions under which it formed. Temperature influences the structure of the ice crystals. Wind carries dust that settles on the surface. Volcanic eruptions deposit ash. And most importantly, the air itself becomes trapped. When snow falls, it contains spaces between the crystals. As more snow piles on top, those spaces shrink. Air becomes isolated in tiny pockets. Eventually, the surrounding ice seals them completely. At that moment, the air inside is cut off from the atmosphere above. It becomes a snapshot of Earth's atmosphere at that specific time. Not an estimate, not a reconstruction, a sample. This is why Antarctic ice cores are so powerful. They allow scientists to measure past concentrations of carbon dioxide, methane, nitrous oxide, and other gases directly. Before ice cores, understanding ancient atmospheres required inference from indirect indicators. Ice cores changed that. They turned speculation into measurement. Extracting these cores is a careful process. Drilling rigs are set up in some of the most remote environments on Earth. The drill descends slowly, cutting through ice and bringing up sections that may be several meters long. Each segment is logged, sealed, and kept frozen to preserve its integrity. Over the course of a drilling campaign, which can take years, cores may reach depths of 3 or 4 kilometers, approaching bedrock. As depth increases, the ice becomes older. Near the surface, layers can often be counted like tree rings. Seasonal variations in snowfall and chemistry create patterns that repeat annually. Deeper down, pressure thins the layers, making individual years harder to distinguish. At that point, scientists rely on a combination of methods to date the ice. Volcanic ash layers provide known time markers. Changes in atmospheric composition correlate with well-established climate cycles. Together, these techniques allow researchers to build a precise timeline. Once cores are extracted, the real work begins. In laboratories, sections of ice are carefully sliced and analysed. Some are melted to release trapped gases. Others are examined for chemical impurities, dust content, and isotopic composition. Each measurement adds another piece to the story. The air bubbles are often the focus, but the ice itself is just as informative. The ratio of different oxygen and hydrogen isotopes in the ice reveals information about temperature at the time the snow fell. Warmer conditions favour lighter isotopes evaporating and precipitating. Colder conditions shift that balance. By measuring these ratios layer by layer, scientists can reconstruct temperature changes over time with remarkable resolution. When these temperature reconstructions are compared with gas concentrations from the same layers, patterns emerge. Over hundreds of thousands of years, temperature and greenhouse gas levels rise and fall together. During glacial periods, when ice sheets expanded and temperatures dropped, carbon dioxide and methane levels were lower. During warmer interglacial periods, they increased. The relationship is consistent and unmistakable. What Antarctica's ice cores reveal is not just that climate changes, but how it changes. They show that transitions between cold and warm states can occur over relatively short geological timescales. Thousands of years, not millions. They also show that once certain thresholds are crossed, feedback mechanisms amplify change. Ice retreats, reducing reflectivity. Oceans release stored carbon dioxide. Warming accelerates. One of the most striking aspects of these records is their regularity. Over the past several 100,000 years, Earth has experienced repeated glacial cycles, roughly every 100,000 years. These cycles align with subtle changes in Earth's orbit and tilt, which alter the distribution of sunlight. On their own, these orbital variations are small, but the ice core record shows how they are magnified by internal climate feedbacks, leading to dramatic shifts. The ice also records sudden events. Volcanic eruptions appear as spikes in sulfur compounds. Some eruptions were large enough to influence global climate, causing short-term cooling. These events can often be matched with historical or geological records elsewhere, allowing scientists to synchronize timelines across continents. Dust layers tell another story. During colder, drier periods, wind carried more dust from exposed land surfaces. That dust settled on Antarctic ice, darkening layers and leaving chemical signatures that point to its origin. Analysis of dust composition reveals changes in wind patterns, vegetation cover, and aridity in distant regions. In this way, Antarctica records not only its own climate, but conditions across much of the planet. As ice cores extended deeper and further back in time, they began to answer questions that had lingered for decades. How stable is Earth's climate system? How tightly are greenhouse gases linked to temperature? How unusual is the current atmospheric composition? The answers, preserved in ice, are clear. For most of the last 800,000 years, carbon dioxide concentrations fluctuated within a relatively narrow range. They rose and fell with temperature, but they never exceeded certain limits. The modern increase stands out sharply against this background. In the uppermost layers of Antarctic ice cores, the change is abrupt. The slope is steep. The concentration jumps beyond anything recorded in the deeper ice. This does not mean that Earth has never been warmer than it is today. It has. But it does mean that the rate and magnitude of atmospheric change in the recent past are unusual in the context of the ice core record. Antarctica does not editorialize, it simply shows what happened. Another important message from deep time concerns variability. Climate is not a smooth curve. It is punctuated by abrupt shifts, pauses, and reversals. Ice cores reveal periods when temperatures changed rapidly, sometimes within a few decades. These events challenge the assumption that climate always responds slowly. They show that under certain conditions, the system can reorganize quickly. Understanding these past abrupt changes helps scientists assess risks in the present. It provides examples of how the climate system behaves under stress. It also highlights the importance of feedbacks involving ice, oceans, and atmosphere. Beyond climate, ice cores preserve evidence of Earth's broader environmental history. Changes in atmospheric oxygen isotopes reflect shifts in global ice volume. Variations in nitrate and ammonia hint at changes in biological activity. Even traces of cosmic dust have been found, linking Earth's history to events beyond the planet itself. What is remarkable is how much information can be extracted from such a simple material, frozen water, and yet that simplicity is deceptive. Ice is an excellent archive precisely because it is chemically stable, physically ordered, and formed incrementally. It captures complexity without distorting it. Working with ice cores requires restraint. Once a core is melted or cut, that portion of the record is gone. Samples are precious. Portions are archived for future analysis using techniques that may not yet exist. Antarctica's ice is not a renewable resource on human timescales. Protecting it is part of the scientific responsibility. There is also a spatial dimension to these records. Ice cores from different locations across Antarctica tell slightly different stories. Coastal regions reflect influences from the ocean. Interior sites capture more isolated atmospheric signals. By comparing multiple cores, scientists can distinguish local effects from global ones. Patterns that appear across the continent are particularly robust, indicating changes that affected the entire planet. As drilling projects push deeper, they approach ice that formed before the current pattern of glacial cycles. Some cores now reach back over 1 million years, offering glimpses of climate behaviour under different boundary conditions. These older layers may help answer questions about why glacial cycles changed in frequency and intensity, and how Earth transitioned into its current rhythm. There's also the question of what lies below the deepest ice cores. Beneath the ice, sediments may preserve even older records, bridging the gap between the frozen era and the time when Antarctica was green. Linking these archives could provide a continuous narrative from forested landscapes to ice-covered deserts, tracing the full arc of the continent's transformation. For now, ice cores remain one of the most direct connections we have to deep time. They allow us to breathe ancient air in a sense, to measure the chemistry of atmospheres long gone. to see how Earth responded to natural forces before humans altered the equation. What they show is not a planet in constant balance, but a planet in motion, stable for a while, then changing, sometimes gently, sometimes abruptly. Antarctica's ice does not soften that message, it preserves it faithfully. Extinction is often imagined as something loud, sudden, a dramatic ending marked by fire, impact, or darkness falling across the world all at once. That image comes partly from how stories are told, and partly from a few exceptional events that truly were abrupt. But most extinction is quieter than that. It unfolds slowly, unevenly, and often invisibly, written not in a single catastrophic moment, but across thousands or millions of years. Antarctica, despite its silence, holds some of the clearest records of this slower kind of disappearance, preserved not in ruins or bones alone, but in snow, ice, and stone. What makes Antarctica unusual is that it records extinction indirectly. You rarely find mass graves of animals frozen in dramatic poses beneath the ice. Instead, you find absence, a thinning of diversity, a gradual fading of signals that once were strong, pollen types that become rarer, then vanish, chemical markers that indicate biological productivity dropping away, sediment layers that shift from organic rich to almost sterile. These changes are subtle, but when read carefully, they tell a story of life retreating step by step from a continent that was becoming less and less hospitable. One of the most important things Antarctica shows us is that extinction does not always come from a single blow. It can come from isolation. As the continent drifted south and ocean currents reorganized, ecosystems that once exchanged species and genetic material with the rest of the world became increasingly cut off. That isolation mattered. When conditions began to deteriorate, there were fewer escape routes. Migration paths closed. Adaptation became the only option, and for many species it was not enough. The first signs of this retreat appear in the fossil record as changes in plant communities. Earlier layers show a rich mix of pollen from multiple tree and shrub species. Over time, that diversity narrows. Certain pollen types decline steadily. Others become dominant for a while, suggesting that a smaller group of species was better suited to the cooling climate. Eventually, even those disappear. The snow that followed sealed those final moments in place. This transition from forested landscapes to barren ones was not instantaneous. It unfolded over millions of years, with periods of relative stability interrupted by cooling pulses. Antarctica's records show that ecosystems can persist for long stretches under stress, adjusting gradually until they reach thresholds they cannot cross. Once those thresholds are exceeded, collapse follows, not as an explosion, but as a long fading. What makes Antarctica especially valuable in understanding extinction is the way its records align climate change with biological response. Ice cores show precisely when temperatures dropped, when atmospheric carbon dioxide levels fell, and when ice sheets expanded. Fossil and sediment records show how life responded to those changes. When the two are matched, patterns emerge. Cooling precedes biological decline. Ice expansion follows. Extinction does not lead climate change, it follows it. This may sound obvious, but it is not always easy to demonstrate elsewhere. On continents that remained biologically active, ecosystems rebounded, reorganized, and masked earlier losses. New species arrived, old ones were replaced. In Antarctica, once life retreated, it rarely returned. The ice locked in the outcome, preserving the moment when a once-living landscape crossed into long-term sterility. Extinction events recorded in Antarctica are also unusual because they are tied less to sudden disasters and more to systemic change. There is no strong evidence that a single asteroid impact or volcanic super-eruption wiped out Antarctic ecosystems. Instead, the primary drivers were temperature decline, changes in precipitation, and the loss of connectivity to other landmasses. This makes Antarctica a case study in how gradual environmental change can be just as decisive as sudden catastrophe. That does not mean sudden events are absent from the record. Ice cores preserve evidence of volcanic eruptions that would have affected climate temporarily. Ash layers appear in the ice, marking eruptions powerful enough to send material around the globe. Some of these events may have added stress to already struggling ecosystems, accelerating decline, but they appear as punctuation marks, not the main narrative. Stone also carries part of this story. Sedimentary rocks beneath Antarctica record shifts in deposition that reflect changing environments. Earlier sediments show signs of river activity, soil formation, and organic accumulation. Later layers shift toward glacial deposits, ground-up rock, and minimal organic content. This change in sediment type mirrors the biological transition. As life retreated, so did the processes that life supports. There is also evidence of extinction written into the chemistry of these sediments. Certain elements are associated with biological activity. Their decline indicates reduced productivity. Isotopic signatures shift as carbon cycling slows and organic matter becomes scarce. These chemical changes do not scream extinction. They whisper it, steadily and persistently. One of the most striking aspects of Antarctica's extinction record is how complete it is. In many parts of the world, extinction is followed by recovery. New ecosystems form. Life returns in altered forms. In Antarctica, recovery did not occur. Once ice sheets became established and temperatures fell below critical thresholds, the continent crossed into a new state that excluded complex terrestrial life almost entirely. That makes the extinction final in a way that is rare on geological timescales. This finality allows scientists to trace extinction with unusual clarity. There is no confusion about whether a species disappeared temporarily or permanently. There is no later overprinting by new biological activity. The ice preserved the endpoint. Antarctica did not forget what it lost. These extinction events also had consequences beyond the continent itself. As Antarctic ecosystems collapsed, species that could migrate did so, dispersing into other southern continents. This movement reshaped biodiversity patterns elsewhere. Lineages that once thrived in Antarctica became confined to narrower ranges. Genetic diversity shifted. Some species survived only because they left early enough. In this way, Antarctica's extinction events were not isolated tragedies. They were part of a broader reorganization of life in the southern hemisphere. Understanding them helps explain why certain plant and animal groups are distributed the way they are today, and why some regions show higher endemism than others. There is also an emotional weight to these records, even if they are read scientifically. Knowing that forests once stood where ice now dominates forces a reconsideration of permanence. Landscapes we think of as eternal are not. Life that seems well adapted can still be outpaced by environmental change if it unfolds over long enough timescales. Antarctica's extinction story is also a reminder that climate does not need to become extreme to be destructive. The continent did not freeze instantly, it cooled gradually. Yet that gradual change was enough to eliminate entire ecosystems. This challenges the assumption that slow change is always manageable. For some systems, the rate matters less than the direction. The snow and ice play a dual role here. They record extinction, and they contribute to it. As ice expanded, it altered surface reflectivity, reinforcing cooling. As glaciers advanced, they destroyed habitats and fragmented what remained. Ice was both archive and agent, preserving evidence even as it erased life. Stone, meanwhile, provides context. Rock layers tell us how long ecosystems persisted before collapse, and how quickly conditions shifted afterward. They show that extinction was not synchronized everywhere. Some regions lost life earlier, others held on longer depending on elevation, proximity to the coast, and local climate. This unevenness adds depth to the story, showing that extinction is rarely uniform. What Antarctica teaches us about extinction is not limited to the past. The mechanisms recorded there are still relevant. Isolation, gradual climate change, feedback loops and threshold effects all operate today. The difference is timescale. What unfolded over millions of years in Antarctica is now being compressed into centuries in some parts of the world. This does not mean history will repeat itself in the same way. Conditions are different, species are different, but the principles remain. Ecosystems have limits. When those limits are exceeded, loss follows, often quietly and often before it is fully recognized. Antarctica's records are valuable precisely because they are unemotional. Ice and stone do not dramatize extinction. They do not frame it as a moment of crisis. They show it as a process, a narrowing, a simplification, a steady reduction until complexity gives way to absence. When people think about the history of life on Earth, the story often jumps abruptly. Dinosaurs dominate one moment, towering, diverse, unmistakable. Then, almost without warning, the narrative shifts forward to mammals, primates, and eventually humans. The space between those two worlds tends to feel compressed, like a few pages torn out of a very long book. We know something happened there. We know it mattered. But the details are often blurred, uneven, or missing entirely. Antarctica sits directly in that gap, not because dinosaurs or early humans lived on its frozen surface as we imagine it today, but because the continent was present, active, and recording environmental change during one of the most transformative stretches of Earth's history. While other regions were eroded, reworked, or biologically overwritten, Antarctica slowly moved into isolation and then froze, sealing parts of that transition in place. What it preserved may help explain how the world moved from a dinosaur-dominated planet to one shaped by mammals and, eventually, us. To see why this matters, it helps to step back and consider how uneven the fossil record really is. Fossils do not form everywhere, and they certainly do not form continuously. They require specific conditions: rapid burial, limited oxygen, and relative stability afterward. Many environments are terrible for fossil preservation. Forest floors are churned by roots and organisms, mountains erode, rivers shift course, coastal regions are repeatedly flooded and exposed. Over tens of millions of years, entire chapters of biological history can be erased without leaving a trace. The period following the extinction of non-avian dinosaurs is one of those unevenly preserved intervals. We know the broad outline. A mass extinction removed dominant species, mammals diversified, birds flourished, flowering plants spread, climate shifted. But when it comes to the details, how fast these changes happened, how ecosystems reorganized, and how different regions responded, the record is patchy. Some places preserve rich sequences, others preserve almost nothing. Antarctica is unusual because it was undergoing a different kind of transformation at the same time. While life elsewhere was recovering and diversifying, Antarctica was drifting south, cooling, and gradually becoming isolated. That combination matters. It means the continent was experiencing global biological change and local environmental stress simultaneously. Those overlapping pressures left signatures that are not easy to find elsewhere. During the late age of dinosaurs, Antarctica was not a frozen wasteland. It supported forests and complex ecosystems, as fossil evidence shows. Dinosaurs lived there too, adapted to polar light cycles much as plants were. When the mass extinction event occurred, Antarctica did not escape its effects. Fossil records suggest that dinosaur species disappeared there along with their counterparts elsewhere, but what followed is where things become especially interesting. In many parts of the world, post-extinction ecosystems were quickly reshaped by surviving species newcomers. Sediments were reworked, new forests grew, rivers shifted, life rebounded, and in doing so, obscured the immediate aftermath. In Antarctica, cooling and isolation slowed that process. Ecosystems were under stress not only from extinction, but from a climate that was becoming increasingly challenging. Recovery did not proceed in the same way. This makes Antarctica a kind of bottleneck in the story of life. It was not a place where diversity exploded after dinosaurs vanished. It was a place where life struggled, adapted, and eventually retreated. That struggle is recorded in fossils, sediments, and chemical signatures that capture how ecosystems responded when recovery was constrained rather than encouraged. One of the key questions in this interval is how mammals rose to prominence. Mammals existed long before dinosaurs disappeared, but they were mostly small and ecologically limited. After the extinction, they diversified rapidly, but this diversification did not happen uniformly across the globe. Climate, geography, and connectivity mattered. Antarctica's fossil record suggests that mammalian expansion there was limited and short-lived. Cooling temperatures and shrinking habitats prevented mammals from establishing long-term dominance on the continent. That absence is informative. It shows that the rise of mammals was not inevitable everywhere. It depended on environmental opportunity. Antarctica lacked that opportunity. Instead of becoming a cradle for mammalian evolution, it became a record of what happens when environmental constraints suppress diversification. Plants tell a similar story. Flowering plants spread widely after the dinosaur extinction, reshaping terrestrial ecosystems. In Antarctica, their spread appears to have been limited and eventually reversed as cooling progressed. Pollen records show shifts in plant communities that reflect stress rather than expansion. Diversity declined instead of increasing. This contrasts sharply with patterns seen in lower latitudes. By comparing these records, scientists can tease apart which aspects of post-dinosaur recovery were driven by global factors and which depended on local conditions. Antarctica acts as a control case. It shows what happens when the usual pathways of recovery are blocked. The climate context is crucial here. The period between dinosaurs and humans includes major climate transitions, including a long-term cooling trend that eventually led to the ice ages. Antarctica played a central role in that shift. As it drifted south and ocean currents reorganized, the continent influenced global heat distribution. Ice sheets grew, sea levels changed. These changes affected habitats worldwide. Antarctica's ice and sediments preserve evidence of how these climate shifts unfolded. Ice cores capture atmospheric composition. Sediments record ocean temperatures. Together they show that cooling was not steady. It occurred in steps, with periods of relative warmth punctuated by sharper declines. These steps correspond to changes in ocean circulation and ice growth, processes in which Antarctica was a major driver. This matters for understanding evolution, because climate change shapes selection pressures. Gradual cooling favours different traits than rapid shifts. Antarctica's record helps establish the timing and pace of these changes, providing context for evolutionary patterns seen elsewhere. Another missing piece in this interval concerns extinction beyond the dinosaurs. The end Cretaceous extinction was not the last major loss of life. The following tens of millions of years saw additional extinctions, many of them linked to climate change. Antarctica preserves evidence of these quieter losses. Pollen diversity declines, marine microfossils change composition, chemical markers indicate reduced productivity. These signals suggest that extinction continued long after the dramatic end of the dinosaurs, reshaping ecosystems in more subtle ways. Because Antarctica became increasingly isolated, it did not receive new species as easily as other continents. That isolation magnified the effects of extinction. Once a lineage disappeared there, it was unlikely to be replaced. This makes the continent's record unusually clear. Losses remain visible rather than being masked by later arrivals. There is also a temporal advantage to Antarctica's preservation. Ice and cold slowed geological processes that would otherwise blur the record. In many regions, sediments from this interval have been eroded or deeply buried. In Antarctica, they were sealed beneath ice before they could be disturbed. This creates the possibility of accessing continuous records that bridge gaps found elsewhere. drilling into sediments beneath Antarctic ice has already begun to reveal sequences that span critical intervals. These cores contain microfossils, organic molecules, and chemical signatures that trace changes in ocean conditions and biological communities across millions of years. They help link the end of dinosaur-dominated ecosystems to the rise of modern ones. What emerges from these records is not a clean break, but a prolonged transition. Dinosaurs vanished relatively abruptly. The world that followed took much longer to stabilize. Antarctica shows that this stabilization was uneven. Some regions became havens for diversification. Others, like Antarctica, became filters, allowing only certain lineages to persist briefly before conditions closed in. This filtering effect may help explain why modern Antarctic life is so limited. The continent did not simply lose life when it froze. It lost life gradually through a series of bottlenecks that eliminated complexity step by step. By the time permanent ice sheets formed, little remained to lose. Understanding this process fills in missing pages of Earth's story. It shows that the space between dinosaurs and humans was not just a time of recovery and progress, it was also a time of constraint, loss, and regional divergence. Antarctica exemplifies the latter. There is also a lesson here about how history is shaped by preservation. We tend to tell stories based on what survives. Regions with rich fossil records appear central, those without seem peripheral. Antarctica challenges that bias. Its importance lies not in abundance, but in absence, in what it did not become, in the pathways it closed rather than opened. As research continues, Antarctica's role in this interval is becoming clearer. It was not a backwater. It was an active participant in global change, influencing climate, recording biological responses, and preserving transitions that elsewhere were overwritten. The missing pages between dinosaurs and humans are not missing everywhere. They are scattered, fragmented, and uneven. Antarctica holds some of those fragments, preserved under conditions that favoured memory over reinvention. Reading them requires patience, indirect methods, and a willingness to accept incomplete answers. But even partial answers matter. They remind us that evolution does not move uniformly toward complexity or dominance. It responds to context. It is shaped by geography, climate, and chance. Antarctica's story shows how a continent can move from supporting dinosaurs to excluding almost all terrestrial life, not through a single disaster, but through a long narrowing of possibilities. The question sounds almost dramatic when phrased this way, as if Antarctica might suddenly overturn everything we think we know. But rewriting a climate story does not mean erasing what came before. It means adding context that was missing, filling gaps that made earlier explanations feel simpler than reality actually is. Antarctica is not waiting to contradict climate science, it is waiting to complete it. For much of modern science, Earth's climate story has been reconstructed from fragments. Tree rings here, ocean sediments there, coral growth bands, cave deposits, lake beds, and ice cores scattered across the globe. Each archive tells a local story very well, but stitching them together into a global narrative has always involved uncertainty. Different records cover different timescales. Some stop abruptly, others are distorted by erosion, tectonics, or biological activity. Antarctica stands apart because it offers something rare: continuity. The interior of Antarctica has remained cold, dry, and stable for immense spans of time. That stability allowed ice to accumulate without melting year after year, layer after layer. It allowed atmospheric gases to be trapped and preserved. It allowed dust, ash, and chemical signals to settle undisturbed. In other words, it created a reference archive against which other records can be compared. That alone gives Antarctica the power to reshape how we interpret Earth's climate history. One of the most important ways Antarctica influences climate science is by anchoring timelines. Many climate records elsewhere rely on relative dating. Layers are older or younger compared to one another, but precise ages can be difficult to establish. Antarctic ice cores, by contrast, often include clear time markers. Volcanic ash layers correspond to known eruptions. Orbital cycles leave predictable signatures. Atmospheric gas changes align globally. These anchors allow scientists to synchronize records from different regions, revealing whether events were simultaneous or staggered across the planet. This synchronization has already changed our understanding of past climate shifts. For example, Antarctic records show that some temperature changes began in the southern hemisphere before appearing in the northern hemisphere, or vice versa, depending on the mechanism involved. This challenges older assumptions that climate change always propagated uniformly from one region. Instead, it reveals a more complex system where oceans, atmosphere, and ice interact in asymmetric ways. Antarctica also forces a re-evaluation of cause and effect. When scientists first noticed the close correlation between temperature and carbon dioxide in ice cores, debate followed. Did carbon dioxide drive temperature change, or did temperature change drive carbon dioxide? Antarctic records show that both processes occur depending on context. In some cases, initial warming triggered carbon release from oceans, which then amplified warming globally. In other cases, changes in atmospheric composition preceded temperature shifts. This nuanced view replaces simplistic narratives with feedback-driven systems. Another area where Antarctica adds depth is in understanding thresholds. Climate does not respond smoothly to forcing. It often remains relatively stable until a boundary is crossed, after which rapid change follows. Antarctic records capture multiple examples of this behaviour. Ice sheets grew gradually, then suddenly expanded. Temperatures declined steadily, then dropped sharply. These transitions are preserved with enough resolution to study their pace and sequence. This matters because thresholds determine risk. If Earth's climate system behaves linearly, small changes produce small effects. If it behaves non-linearly, small changes can trigger large responses once limits are reached. Antarctica provides empirical evidence that non-linear behaviour is not theoretical. It has happened repeatedly in Earth's past. The continent also reframes how scientists think about ice itself. Ice is often treated as a passive responder to climate, growing when cold and shrinking when warm. Antarctica shows that ice can be an active driver. As ice sheets expanded, they altered planetary reflectivity, increasing the amount of sunlight reflected back into space. They changed sea level, reshaping coastlines and ocean circulation. They influenced atmospheric patterns. In doing so, they reinforced the very conditions that allowed them to grow. This feedback role means that ice is not just a symptom of climate change, it is a participant. Antarctica, hosting the largest ice sheet on Earth, is therefore not just recording climate history, it is shaping it. Any attempt to understand past or future climate without fully accounting for Antarctic ice dynamics is incomplete. Antarctica's position also gives it disproportionate influence. Sitting at the bottom of the world, surrounded by ocean, it plays a key role in regulating global circulation. The Southern Ocean acts as a major sink for heat and carbon dioxide. It connects the world's major ocean basins, allowing water to circulate between them. Changes in Antarctic ice and freshwater input affect this circulation, with consequences that ripple outward. Sediment cores taken from the seafloor around Antarctica show how these ocean processes evolved over time. They record shifts in nutrient availability, plankton communities, and carbon storage. When combined with ice core data, they reveal how changes at the pole influenced productivity and climate far beyond it. Antarctica emerges not as an isolated region, but as a central node in Earth's climate network. There is also the matter of time depth. Many climate discussions focus on the past few thousand years, sometimes the past 100,000. Antarctica pushes that perspective much further back. Some ice cores now extend beyond 1 million years. Beneath the ice, sediments preserve even older records, potentially spanning tens of millions of years. These archives capture climate states that no longer exist, including periods when carbon dioxide levels were much higher and ice sheets smaller or absent. Studying these past states allows scientists to test climate models under conditions very different from today. Models that accurately reproduce Antarctic records gain credibility. Those that fail reveal gaps in understanding. In this way, Antarctica acts as a proving ground for climate theory. One of the most powerful contributions Antarctica makes is providing context. It shows that Earth's climate has always changed, but not randomly. Changes follow patterns governed by physics, chemistry, and feedbacks. The ice shows that greenhouse gases matter. It shows that orbital variations matter. It shows that ice, oceans, and atmosphere are tightly coupled. None of this undermines climate science. It strengthens it by grounding it in evidence that spans deep time. At the same time, Antarctic records highlight what is different about the present. When modern atmospheric gas concentrations are placed alongside ancient ones preserved in ice, the contrast is stark. Not because the planet has never experienced high carbon dioxide levels before, but because the speed of change is unusual. Antarctica does not tell us what to think about that difference, it simply makes it visible. There is also a more subtle way Antarctica rewrites the climate story, by reminding us of uncertainty. Even with detailed records, interpretation is challenging. Ice layers thin with depth, signals overlap, processes interact. Scientists must make careful assumptions and test them repeatedly. Antarctica teaches humility. It shows that Earth's system is complex, and that certainty must be earned, not assumed. This humility is productive. It drives refinement rather than complacency. As new cores are drilled and new sediments analysed, interpretations evolve. Early conclusions are adjusted, models improve, the story becomes richer, not simpler. Antarctica also influences how scientists think about future climate change. By studying how ice sheets responded to past warming events, researchers gain insight into potential responses to current warming. Some past periods saw significant ice retreat, at temperatures not dramatically higher than today's. Others show surprising stability. Understanding why outcomes differed requires detailed knowledge of bedrock topography, ocean conditions, and ice dynamics, all of which Antarctica helps provide. Importantly, Antarctica's role in rewriting the climate story is ongoing. The continent is not finished revealing its archives. Large areas remain unexplored. Subglacial sediments are only beginning to be sampled. Deep ice drilling projects continue to push boundaries. Each new dataset has the potential to clarify or complicate existing narratives. There is also a human dimension to this rewriting. Climate stories shape policy, perception, and priorities. A more complete understanding of Earth's past informs how societies assess risk and responsibility. Antarctica's records do not dictate decisions, but they inform them by expanding the frame of reference. What emerges from all this is not a single revised story, but a layered one. Earth's climate history becomes less like a straight line and more like a woven fabric, with Antarctica providing threads that were previously missing. These threads connect events across hemispheres, link atmosphere to ice, and tie biological change to physical processes. The idea that Antarctica could rewrite Earth's climate story is therefore not about surprise, it is about completeness. Without Antarctica, the story is fragmented. With it, patterns become clearer, timelines align, and mechanisms are revealed. Long before Antarctica was measured, sampled, or even seen, it already existed in the human imagination. Not as ice, not as a scientific problem, but as an idea, a blank space that demanded to be filled. Humans have always been uneasy with empty maps. Where knowledge fades, imagination steps in, quietly at first, then with increasing confidence. Antarctica, more than any other place on Earth, became a canvas for that process. For centuries, people believed there had to be something at the bottom of the world. Ancient thinkers reasoned that the Earth needed balance. Too much land in the north, they thought, would tip the world unless it was countered by land in the south. This was not observation. It was symmetry, a philosophical comfort with the idea that nature should be orderly, even if no one had proof. And so maps began to show a vast southern continent long before anyone could verify its existence. These early depictions were not icy, they were lush. Rivers, mountains, forests, even cities appeared in some illustrations. The imagined southern land was often drawn as fertile and welcoming, a mirror of known continents rather than their opposite. This tells us something important about how humans project familiarity onto the unknown. When faced with absence, we tend to duplicate what we already understand. As navigation improved and explorers pushed farther south, the imagined continent slowly shrank, retreated, and shifted shape. Each failed expedition trimmed its edges. Each new coastline forced cartographers to redraw their assumptions. But even as Antarctica became more real, it remained incomplete. The interior stayed blank long after the coasts were mapped, and that blankness continued to invite speculation. What makes Antarctica different from other unexplored regions is how long that blankness persisted. By the time most of the world was charted, Antarctica remained largely unknown. Dense jungles had been crossed, deserts mapped, mountain ranges climbed. Yet Antarctica resisted penetration. Ice, cold, and isolation slowed progress to a crawl. This prolonged uncertainty created fertile ground for myth. Some imagined lost civilizations hidden beneath the ice. Others speculated about ancient advanced societies that had vanished when the continent froze. Stories of sunken cities, forgotten technologies, and vanished races found a natural home there. Antarctica's inaccessibility made such claims difficult to disprove, and its silence made them feel plausible to those inclined to believe. These myths were not born solely of fantasy. They were fueled by fragments of truth misunderstood or exaggerated. Fossil discoveries showing that Antarctica was once green-fed narratives of a fallen world. Ancient maps that depicted land where ice now dominates were interpreted as evidence of lost knowledge rather than educated guesses. Even geological features detected beneath the ice were sometimes folded into speculative stories far removed from science. Maps played a central role in this process. A map is never just a representation of space, it is an assertion of understanding. Blank areas signal ignorance, but they also signal possibility. For centuries, Antarctica was the largest blank space on Earth's maps. That alone made it special. It was the last place where anything could still be imagined. As scientific exploration advanced, myths did not disappear. They adapted. When it became clear that Antarctica was ice-covered, speculation moved beneath the ice. What lies below became the new question. Subglacial lakes, buried mountains, and ancient sediments were recast in popular imagination as hiding places for lost worlds. The more science revealed complexity beneath the ice, the more room there seemed to be for imaginative elaboration. This tendency is not unique to Antarctica. Humans have always placed myths at the edges of the known world. Sea monsters inhabited uncharted oceans, dragons guarded unknown mountains. But Antarctica amplified this pattern because it resisted domestication. It did not become familiar with time. It remained distant, inhospitable, and largely untouched. There is also a psychological dimension to why Antarctica attracts these ideas. It represents a kind of temporal distance as well as spatial distance. It feels outside of ordinary time. No cities rise there. No civilizations layer over one another. Human history barely touches it. In a world where almost every place carries visible signs of human presence, Antarctica feels like a place before us, or after us, depending on how one looks at it. This sense of temporal otherness encourages narratives about lost epochs. If a place feels untouched by modernity, it becomes easier to imagine it as a remnant of something ancient. Antarctica's ice reinforces this impression. Ice preserves, ice suspends, ice delays change. These qualities make it easy to imagine that something beneath it has been waiting, unchanged, for ages. Science itself has contributed, unintentionally, to this mystique. When researchers describe landscapes buried beneath kilometers of ice, or lakes isolated for millions of years, the language naturally sounds dramatic. It speaks of hidden worlds, sealed environments, and deep time. These descriptions are accurate, but when filtered through popular culture, they take on a mythic tone. The difference between scientific mystery and myth lies not in the presence of the unknown, but in how it is treated. Science approaches the unknown cautiously, incrementally, accepting uncertainty. Myth fills it decisively, often emotionally. Antarctica sits at the boundary between these approaches. It offers genuine unknowns that science is still working to understand, and that makes it vulnerable to imaginative overreach. Another reason Antarctica attracts lost world narratives is that it disrupts linear history. Most places on Earth show continuous occupation or repeated cycles of use. Antarctica does not. There is no visible progression from ancient to modern. That absence creates the illusion of a break in time. It feels plausible at an emotional level that something important happened there and was then erased. This illusion is reinforced by the fact that Antarctica was once very different. Knowing that forests once grew there invites speculation about what else existed. If trees and animals lived there, why not people? If not people, then something else. The leap from ecological change to cultural speculation is not logical, but it is emotionally intuitive. Maps from different eras compound this effect. Early maps showing land where ice now exists are sometimes interpreted as evidence that Antarctica was ice-free in human times, despite clear geological evidence that the freezing occurred long before humans evolved. These maps are better understood as products of incomplete information and educated guesswork, but myth thrives on ambiguity. There is also a deeper human tendency at work. We're drawn to the idea that the past was richer or more mysterious than the present. Lost golden ages, vanished knowledge, forgotten wisdom. Antarctica, with its preserved past and apparent emptiness, fits neatly into that pattern. It becomes a symbol of what we imagine we have lost, not just geographically, but culturally. Yet when science examines Antarctica closely, a different story emerges. Not one of sudden disappearance, but of gradual transformation. Not of civilizations wiped away, but of ecosystems retreating under long-term pressure. The reality is slower, quieter, and less dramatic than myth, but no less profound. Understanding this difference matters because myths can distract from the real significance of Antarctica. The true lost worlds beneath the ice are not cities or technologies. They're climates that no longer exist, ecosystems that cannot return, atmospheric conditions that shaped life in ways we're only beginning to understand. These are losses on a planetary scale, not a narrative one. There is also a risk in romanticizing Antarctica as a place of hidden wonders waiting to be revealed. That framing can encourage a sense that the continent exists to be uncovered, exploited, or claimed. In reality, Antarctica is protected by international agreements precisely because of its fragility and scientific value. Treating it as a stage for fantasy undermines the seriousness of preserving what remains. At the same time, it would be wrong to dismiss the imaginative pull of Antarctica entirely. Curiosity and imagination are closely linked. The desire to know what lies beneath the ice, whether driven by science or story, comes from the same place. The difference lies in how that curiosity is directed. Science channels it into careful measurement, patient exploration, and respect for uncertainty. Myth channels it into certainty without evidence. Antarctica teaches us the value of the former by resisting the latter. The continent does not reward haste or assumption. It yields information slowly and often in ways that complicate rather than simplify our understanding. There is something instructive in that. In a world increasingly saturated with information, Antarctica reminds us that not knowing can be productive, that some questions take generations to answer, that some stories unfold over timescales far longer than human attention spans. When myths about lost worlds persist, they often say more about the present than the past. They reflect anxieties about decline, fascination with origins, and discomfort with uncertainty. Antarctica becomes a mirror for those feelings because it remains unresolved. Maps today are no longer blank in the way they once were. Satellite imagery has filled in coastlines. Radar has revealed bedrock. Models predict ice flow and climate response. And yet, the continent still resists total comprehension. There are still gaps, still unanswered questions, still places no human has ever stood. The difference now is that those gaps are approached with humility rather than projection. As scientific knowledge grows, myths lose their footing, but the sense of wonder does not have to disappear with them. In fact, understanding how extraordinary Antarctica truly is makes the imagined lost world seem unnecessary. The real story is already vast enough. The continent does not hide ancient cities, it hides evidence of planetary change. It does not conceal forgotten technologies, it preserves climates, landscapes, and transitions that shaped life across the globe. These are not stories we invented to fill a void. They are stories written by the Earth itself, waiting to be read carefully. There is a point in any long investigation where confidence gives way to something quieter. Not uncertainty exactly, but awareness. A recognition that the more clearly you see, the more edges appear around what you do not yet understand. Antarctica has brought climate science, geology, biology, and even human imagination to that point. For all the maps refined, cores drilled, and models improved, the continent keeps revealing how provisional our understanding still is. This is not a failure of science. It is a consequence of scale. Antarctica operates on spatial scales that are difficult to fully sample, and on timescales that dwarf recorded history. Even the most ambitious research projects only touch fragments. A few deep ice cores spread across thousands of kilometers, radar lines stitched into continent-wide maps, sediment cores taken from narrow windows where access is possible. These data are extraordinarily valuable, but they are still sparse relative to the size and complexity of the system they describe. One of the most important things scientists are only just beginning to understand is how interconnected Antarctica's internal systems truly are. For a long time, ice sheets were studied primarily as surface features: thickness, temperature, accumulation rates, flow speed. The focus was on what could be measured directly or inferred from above. What is becoming increasingly clear is that the most influential processes often occur out of sight, at the base of the ice, or within the ice itself. Subglacial water systems, for example, were once treated as curiosities, isolated lakes, interesting but peripheral. Now they are understood as dynamic networks that interact with ice flow, bedrock heat, and even ice sheet stability. Water moves beneath Antarctica over vast distances, linking regions that appear unrelated on the surface. Changes in one area can propagate through this hidden system, altering conditions elsewhere in ways that are only beginning to be modelled. Closely tied to this is the growing recognition of how important bedrock topography is. The shape of the land beneath the ice determines how ice responds to warming, where it accelerates, where it stabilizes, and where it becomes vulnerable to runaway retreat. For decades, models assumed simplified bedrock representations because detailed data were unavailable. As mapping improves, those assumptions are being revised, sometimes dramatically. In some regions, bedrock slopes downward inland, creating conditions where retreat can feed on itself. Once ice thins and grounding lines move, warmer ocean water can penetrate farther beneath the ice, accelerating melt. These mechanisms are now understood in principle, but their real-world behaviour depends on fine details of topography, sediment composition, and water flow that remain incompletely mapped. Another area of emerging understanding involves the role of the Southern Ocean. Antarctica does not exist in isolation from the ocean that surrounds it. The Southern Ocean absorbs vast amounts of heat and carbon dioxide, acting as a buffer for global climate. But that buffering capacity is not infinite, and it is not constant. Changes in wind patterns, freshwater input from melting ice, and ocean circulation all affect how efficiently heat and carbon are taken up. Sediment cores and modern measurements suggest that the Southern Ocean has shifted between different modes of circulation in the past. Some of these shifts appear to coincide with major climate transitions. Understanding exactly how and why these changes occurred is still an active area of research. The answers matter because similar shifts could occur again under modern warming. There is also growing interest in the coupling between Antarctic ice and atmospheric circulation. The continent's extreme cold influences the formation of dense air masses that drive global wind patterns. As ice changes, those patterns may shift, with consequences far beyond the polar regions. Evidence of past atmospheric reorganization is preserved in ice core chemistry and dust records, but interpreting it requires disentangling multiple overlapping signals. Biology beneath the ice is another frontier where understanding is just beginning. The discovery of microbial life in subglacial environments challenges assumptions about the limits of life and the conditions required to sustain it. These ecosystems, if they exist widely, operate on timescales and energy budgets unlike surface life. Metabolism may be extraordinarily slow. Reproduction may occur over centuries. Evolutionary pathways may differ fundamentally from those we are familiar with. Studying such systems is difficult not only because of access, but because of interpretation. Detecting DNA or metabolic byproducts does not automatically reveal how communities function, how long they have persisted, or how resilient they are to change. Each new finding raises additional questions rather than closing the book. There is also the matter of deep time continuity. Ice cores provide detailed records extending back hundreds of thousands to over 1 million years. Sediments beneath ice sheets extend further, potentially tens of millions of years. Linking these archives into a single continuous narrative is a challenge that scientists are only beginning to tackle. Doing so requires precise dating, careful correlation, and an understanding of how different archives respond to the same events. A temperature shift recorded in ice may appear differently in marine sediments. A biological change evident in pollen may lag behind atmospheric change. Integrating these signals into a coherent timeline is complex, and interpretations continue to evolve. One of the most profound realizations emerging from Antarctic research is how non-linear Earth systems are. Changes do not always scale proportionally with forcing. Small perturbations can produce large effects if they interact with the right feedbacks. Large changes can sometimes be absorbed with surprisingly little immediate impact. Antarctica's records are full of such surprises. For example, there are periods in the past when carbon dioxide levels were relatively high, yet ice sheets persisted. In other periods, modest changes coincided with significant ice retreat. These discrepancies highlight the importance of boundary conditions. Continental configuration, ocean circulation, and existing ice volume all influence outcomes. Climate sensitivity is not a single number, it is context dependent. This realization complicates predictions, but it also improves them. Rather than relying on simplified assumptions, scientists are now building models that incorporate more of Antarctica's internal complexity. These models are computationally demanding and data-hungry, but they represent a more realistic approach. Another area where understanding is evolving concerns rates of change. Ice cores show that some climate transitions unfolded rapidly by geological standards, within decades or centuries. Others took millennia. Identifying what distinguishes fast transitions from slow ones is a major research focus. The answer likely involves thresholds, feedback strength, and the interaction between ice, ocean, and atmosphere. Antarctica's role in sea level change is also an area of ongoing refinement. It is clear that Antarctic ice sheets contributed to past sea level fluctuations, but quantifying their exact contribution during specific periods remains challenging. Different regions of the continent responded differently to warming, and regional responses did not always align in time. Modern observations are adding another layer to this understanding. Satellite measurements show changes in ice thickness, flow speed, and grounding line position. Some regions are thinning rapidly, others remain relatively stable. Interpreting these trends in the context of long-term behaviour requires caution. Short-term variability can obscure longer-term trajectories. There is also the question of irreversibility. Some changes, once initiated, may not be easily reversed even if conditions stabilise. Past records suggest that ice retreat can reach points where regrowth is difficult or impossible under the same climate conditions. Identifying these tipping points is critical, but they are not always obvious in advance. Human influence adds further complexity. The climate states preserved in Antarctic records developed without industrial forcing. While they provide essential context, they are not perfect analogues for the present. Modern warming is occurring alongside land use change, altered atmospheric composition, and other factors that have no direct precedent. Antarctica helps define the boundaries of natural variability, but it does not offer simple predictions. What scientists are only just beginning to understand, then, is not a single missing fact, but the full dimensionality of the system. Antarctica is not a passive archive or a single variable problem. It is a coupled system where geology, ice, water, atmosphere, ocean, and life interact across scales of space and time. There's also a cultural shift underway in how Antarctic science is approached. Earlier eras focused on exploration and discovery, on filling in blanks. Today's work emphasizes integration, connecting data sets, reconciling models with observations, understanding processes rather than just documenting features. This shift reflects maturity in the field, but it also reveals how much remains unresolved. Even the basic question of how stable Antarctica's ice sheets truly are under current conditions does not have a single answer. Stability varies by region. It depends on local topography, ocean access, and ice dynamics. Some parts may persist for centuries with little change. Others may respond more quickly. Antarctica does not behave as a single unit, and recognizing that is part of the learning process. There is humility embedded in this stage of understanding. Antarctica has resisted definitive statements at every turn. Each time scientists thought they had grasped its behaviour, new data introduced nuance or contradiction. This pattern is not discouraging, it is instructive. It reminds us that Earth's systems are complex because they are alive with interaction, not because they are poorly understood. As research continues, technologies improve. Autonomous instruments monitor ice and ocean conditions year-round. Satellites provide continuous coverage. Drilling techniques become cleaner and deeper. Data sharing increases. These advances will undoubtedly sharpen understanding, but they will also reveal new layers of complexity. Antarctica will not suddenly become simple, and perhaps that is the most important thing we are beginning to understand. The value of Antarctica lies not in delivering final answers, but in forcing better questions. It teaches scientists to think in systems, to respect uncertainty, and to consider long-term consequences. It challenges assumptions built from incomplete records elsewhere. As attention slowly returns from deep time to the present moment, there is often a temptation to tie everything together neatly, to resolve uncertainty into a lesson or a conclusion. Antarctica does not lend itself to that kind of closure. Its story does not end. It does not pause conveniently for reflection. It continues, quietly and persistently, whether we are paying attention or not. Drifting back to the present does not mean leaving the past behind. It means realizing how much of that past is still active, still shaping what unfolds now. Antarctica's influence has never been confined to the eras it recorded. The processes that buried forests, reshaped mountains, sealed lakes, and locked atmospheres into ice are the same processes that continue to operate today. They move slowly, but they move continuously. Ice still flows, snow still accumulates, water still circulates beneath the surface, heat still rises from the earth below. The continent is not a relic. It is an active system carrying the memory of its own transformation forward in time. What changes as we return to the present is our position within that system. For most of Antarctica's history, humans were not a factor. The continent's shifts were driven by tectonics, orbital cycles, ocean circulation, and atmospheric chemistry evolving without deliberate influence. That is no longer entirely true. Human activity now affects the same variables Antarctica responds to, particularly atmospheric composition and global temperature. The difference lies not in the mechanisms, but in the pace and origin of change. This is where Antarctica's long memory becomes especially important. The ice does not react to intentions, it responds to conditions. Past ice sheets expanded and retreated based on thresholds being crossed, feedbacks being triggered, and balances being disrupted. Those thresholds still exist, they are not theoretical. They are written into the continent's structure and history. The question is not whether Antarctica can change. It has changed many times before. The question is how, where, and how quickly. One of the most sobering realizations from Antarctic research is that stability can be misleading. Long periods of apparent equilibrium can mask underlying vulnerability. Ice sheets can appear steady for thousands of years, then respond rapidly once certain conditions align. The geological record shows this clearly. There are stretches of time where little seems to happen, followed by transitions that unfold much faster than expected. This pattern matters now because modern observations often focus on short time windows. Satellite records span decades. Instrumental climate data covers a century or two at most. Against that backdrop, Antarctica can appear slow to respond, reinforcing a sense of distance or delay. But when placed in the context of its own history, that apparent slowness looks different. Change in Antarctica often begins quietly, in places far from view, before becoming visible at the surface. Subtle thinning at grounding lines, small increases in basal melting, changes in subglacial water flow. These are not dramatic events on their own, but they are the kinds of shifts that have preceded larger transitions in the past. Antarctica's history teaches that outcomes are often determined long before they are obvious. Carrying the past with us also means recognizing how interconnected the present world is with Antarctic processes. The continent influences sea level, ocean circulation, and atmospheric patterns. Changes there do not remain there. Meltwater affects ocean salinity. Ice loss alters circulation pathways. These effects propagate outward, shaping conditions far beyond the polar regions. At the same time, Antarctica remains a place where the past is unusually accessible. Ice cores, sediments, and buried landscapes provide context that few other regions can offer. This makes the continent a reference point, a kind of baseline against which present changes can be compared. Without Antarctica's records, it would be much harder to distinguish between natural variability and unprecedented change. There is also a quieter aspect to carrying the past forward. Antarctica reminds us that Earth's history is not a story of continuous improvement or inevitable progress. It is a story of adaptation, constraint, loss, and reorganization. Entire ecosystems flourished and vanished without human awareness. Climate states persisted for millions of years, then gave way to new regimes. Stability was temporary, change was constant. This perspective challenges modern assumptions about permanence. Coastlines feel fixed, ice sheets feel immovable, climate zones feel familiar. Antarctica shows how conditional those impressions are. It does not argue that dramatic change is imminent everywhere, but it demonstrates that the planet has always been capable of reorganizing itself when conditions allow. At the human scale, this can feel unsettling. We are accustomed to thinking in decades or lifetimes. Antarctica asks us to think in millennia and millions of years, without losing sight of how present actions fit into that arc. The ice does not judge those actions, it records their effects. There is also a sense of responsibility that emerges when we understand Antarctica's role more clearly. Not responsibility in a moral or abstract sense, but responsibility grounded in consequence. What happens to the continent does not stay isolated. Its response to changing conditions will shape outcomes that extend far beyond its boundaries. Yet Antarctica is not fragile in the way we often imagine fragility. It is resilient, but not invulnerable. It has endured enormous change in the past. It has rebuilt itself into new states. But those states were not interchangeable. Each transition closed some possibilities and opened others. Once forests vanished, they did not return. Once ice sheets stabilized, they reshaped global systems for millions of years. Understanding that history reframes present discussions, it shifts focus away from whether change is natural or unnatural toward how systems respond to forcing regardless of its source. Antarctica's archives do not assign blame, they reveal patterns. Returning to the present also means acknowledging how incomplete our understanding still is. Large portions of Antarctica remain poorly mapped. Subglacial environments are only partially explored. Deep sediment records are sparse. Models continue to improve, but they are still approximations. This uncertainty is not a weakness. It is an honest reflection of the complexity involved. Antarctica encourages a different relationship with knowledge, one that values patience over certainty, accumulation over immediacy. Scientific progress there rarely arrives as breakthroughs that overturn everything. It arrives as refinements, corrections, and slow expansions of context. That pace mirrors the processes being studied. There is something fitting about that. A continent shaped by slow accumulation teaches us slowly. A place that preserved history by freezing it reveals that history incrementally. Antarctica does not reward urgency. It responds to care. As we drift back fully into the present, the image of Antarctica shifts. It is no longer just the end of the world, or a symbol of extremes, or a blank space filled by imagination. It becomes something quieter and more substantial. A record keeper, a regulator, a participant in Earth's ongoing story. The past carried within it is not sealed away. It informs how ice flows today. It shapes how water moves beneath the surface. It influences how the continent responds to warmth and cold. Antarctica does not remember passively. Its memory is active, embedded in structure and process. In that sense, carrying the past with us does not mean holding on to nostalgia or fear. It means recognizing continuity. The conditions that shaped ancient climates and extinctions are not gone. They operate under new configurations, interacting with new influences, but they obey the same physical principles. This realization does not demand a particular emotional response. It does not require alarm or reassurance. It asks for attentiveness, for an understanding that Earth systems respond to what they're given, not to what we expect or hope. Antarctica offers perspective that is difficult to find elsewhere. It stretches time until urgency feels different. It reveals how small changes accumulate. It shows how silence can hold information. It reminds us that absence can be as informative as presence. As attention settles back into the now, the continent remains where it has always been, turning slowly beneath the sky, ice moving inch by inch toward the sea. It does not hurry. It does not pause. It continues to carry its past forward, layer by layer, into a future that is not yet written. And in paying attention to that quiet continuity, there is space to think differently about our own moment. Not as a dramatic turning point set apart from history, but as one more layer forming, influenced by what came before and influencing what comes next. Antarctica does not ask us to draw conclusions. It invites us to stay with the story a little longer, to notice how deeply the present is entwined with the past, and how much of that past is still very much alive beneath the ice, moving steadily, patiently, into whatever comes next.